In the series of videos, we are solving GATE BM 2021 questions. Here we have the aptitude session. Okay, so this is GATE BM 2021 questions, and we are solving the questions in sequence based on the official question paper and answer key. The first 5 questions are multiple choice questions. That is, out of the 4 options, you have to pick one. And if you do it correctly, you will get 1 mark. If your choice is incorrect, you get a negative 1/3. Okay. So the first question is a basic English question. Arun and Aparna are here. We are given like 4 sentences. Which of the above sentences are grammatically correct? Okay. In this particular case, we want correct statements. Sometimes they do ask incorrect statements. Here we want which of the statements are correct. Option 1, Arun and Aparna are here. Yeah, Arun and Aparna is plural, and the correct form of be here is are. Okay? So or is this statement is correct. Arun and Aparna is doesn't fit here. Okay, is will show up if it's a singular subject. Okay, so this is incorrect. And then for the sake of being strategic about this answer, let's say we don't know whether 3 or 4, which of these 3 or 4 is correct at this stage. We just know for sure that 1 is correct. Can we do something very clever at this stage? That is, we know 1 is correct. We are unsure about 3 and 4. Arun's family is here. Arun's family is here. There is something that clever that you could do here. So eliminate options that doesn't have 1. So C is incorrect. D is incorrect. So you have eliminated 2 options at this stage, which means if we were to blindly guess between A and B, you are likely to get positive marks. Okay, that's just a small strategy here. But let's look at the sentences. Arun's families is here. Arun belongs to one family, so this families doesn't make sense here. Arun's family is here. Yeah, this makes sense. So the correct option is 1 and 4. That is option D. Great. A very basic question from English. Second question from GATE BM 2021. This question, we have given some image, some axis, x-axis, y-axis, mirror image of the above text about the x-axis. So we are given an image and they want the mirror image for that. And in this case, they want the mirror image about x-axis. That is also known as water image. The normal mirror image is about y-axis. That's known as a mirror image. Okay. So what we want is this. We are given 4 options. We could either draw the mirror image and then try to map it, try to eliminate incorrect answers and pick them. Whichever works for you, pick that one. Let me draw the mirror image over here. So if you look at this, how will the reflection look in water? Okay, that's what you should answer. So it's going to be P is going to be this, H is going to be H, Y is going to be like this, L is going to be like this, A is going to be like this, X will be X, I will be I, and S will be like this. So which of these images matches this? P is P as such. Okay, it's not a mirror image, so this is incorrect. Okay, we have P, H, Y, L, A, X, I, and yes. Okay, this is correct. We can actually, because it's just one choice that's correct out of 4, we can pick option B is the correct answer right now. But just to double check, make sure these 2 are incorrect. P's mirror image, this is not the mirror image, right? Okay, so this is incorrect. We can just looking at this word letter, we can say it's incorrect. How about option D? Okay, this is mirror image about x-axis, H, Y, L. Pretty much the same as the things in option A. The first difference shows up with this yes. Yes is written as such, right? Yes is yes here. There is no mirror image. So this is correct. This is incorrect. So the correct option is option B. Third question from GATE BM 2021. 2 identical cube-shaped dice with each faces numbered 1 to 6 or rolled simultaneously. So we have two dice that has numbers 1 to 6. Probability that even number is rolled out on each of the dice. Okay, let's call dice, the two dice is dice A and B. So we should get an even number in both the dice. Look at what happens, what is the probability of getting even number in one die. Okay, out of 1, 2, 3, 4, 5, 6, numbers could be 2, 4, 6. So the probability is 3 out of 6, that is half, to get a even number in one die. And to get an even number in die, the other die, again it's half. Okay, to get an even number in both the die, okay, so this half and half multiplies. So the answer we want is 1 by 2 into 1 by 2. Okay, so each die or both the dies, so this word says they have to be multiplied. So the correct answer here is half times half, which is 4. Now, fourth question from KPM 2021. We are given two operators, not plus minus, two operators, operator 1, operator 2. So given any two numbers, they are defined like this. That is, P operator on Q, this operation says P minus Q. P, this operation on Q essentially says it's P times Q. So take any two numbers, this operation says divide second number from first number. This says multiply both the numbers. We have to find what this expression is. This is just replace all these operators for the standard symbols we know, and then you can get the answer. So this is 9. The two operators here, the two operators here are 9 and the term that's inside the bracket. So 9 minus the term inside the bracket, 6 operator on 7. This operation means product. So 6 times 7, and then this operation again means minus. Okay, and 7 times 6 operator on 5. This operation is 6 minus 1. So I have taken this, replaced all these operators with known symbols. Now just evaluate what this is, we should get the answer. So this is 9 minus 6 times 7, it's 42. What is that? 9 minus 42. I suppose it's minus 33. And then we have 6 minus 5 is 1. So 7 times 1 is 7. So this is minus 7. We have minus 40. Correct answer here is option D. Simple math aptitude question. Question number 5 from GatePM 2021. 4 persons PQ, R and S of seat are to be seated in a row. So this is seating arrangement problem. Or should not be seated at the second position from the left end of the row. So one condition is given. Number of distinct seating arrangement is possible. So I find it just 4 people, just one condition. It's very, very easy to visualize that. Let's say this is a left end of the row. We have 4 positions for PQRS, right? So R should not be seated at the second position. So R could be here, or he could be here. So he isn't allowed in this position. Similarly, R could be here, right? So how many ways can PQ are seated in this first case? This corresponds to 6 cases, right? That is 3 times 2 times 1. How about this thing? Again, PQS can be seated in these 3 seats based on, again, 6 cases. 3 times 2 times 1. And again, if R is seated here, PQ and S can be seated here in 6 cases. So the total number of cases in which distinct seating arrangements that are possible is 6 plus 6 plus 6. That is this case or this case or this case, which means 6 times 3, which is 18. C is the correct answer. Simple seating arrangement question. Okay, so now we are discussing GatePM 2021 questions. We are heading to 2 more questions in the aptitude part. So each question, all these questions are multiple choice. So only 1 out of the 4 options are correct. They carry 2 marks. And the wrong answers carry, of course, minus 2 by 3 marks. Okay, on a planar field, you traveled 3 units east from a point to, okay, so this is north, south, east, west problem. So it helps to draw a simple axis, right? Or so I have drawn an XY axis. Let's call this north, south, and of course east and west at this point are east and west. So wherever you start, there is this point O. Let's make it the origin to keep things simple. Okay, you start at point O and then travel 3 units to the east. So this is 3. This is 3 in the direction east. Great. Next, you travel 4 units south to arrive at point P. Okay. So point P is somewhere over here. You travel south. Okay, and this is point P. Now, then you travel from P in the northeast direction such that you arrive at the point 6 units east of point 2. Okay, this is the second time I am reading the sentence. And the first time I read it, I realized the sentence could be slightly ambiguous. That is, you might think going in the northeast direction means actually going at an angle at 45 degrees. No, that is not the case. Notice where you end up at. You essentially, you go northeast, that is somewhere along this direction, and you end up 6 units east of point 2. So take point 2, say 6 units east. Okay, so it's along this line, you end up here. So this is 3, so this is 3, so that the total is 6. Notice this travel is not along 45 degrees. Okay, that's the first thing. Northeast, this is northeast direction, but not, along a 45 degree angle. So that you end up at a point 6 from 6 units from point 2. Next, you travel northwest direction so that you arrive at point Q, that is 8 units north of point P. So this is 3. I suppose we travel down by 4 units. Now we travel along northwest, again not necessarily in the 45 degree angle, but we end up at 8 units, which means we end up somewhere over here, so that this distance is 4. Okay, so this is where we travel, and this point is known as Q. Distance of point Q to point O. So we want the distance between this and this. It's very, very simple. So this is right angle. So this is 3, this is 4. We know this is 5. Notice this is 3, this is 4, this is 3, this is 4. So this distance is just 5. So C is the correct answer. So only thing is traveling northeast need not happen along 45 degree lines. And then if you interpret the statement correctly, it's a very simple problem. And know what is north, south, east, west directions are. Question number 7 from GATE BM 2021. This is a simple text inference problem. A small paragraph is given, and I think 4 statements are made on that. We have to pick one correct option. Okay, so the author said, so one tip here, you could either read the paragraph first, or you could read the options first and then start looking at the paragraph. Reading the option first makes sense if the paragraph is like too lengthy, right? You can look for facts and all that. Okay, which of the 4 facts should we be focusing on? In that case, it's very helpful. In this case, it's a short paragraph. As you read it, try to make a 1 or 2 line summary of it so that you can pick the correct option here. Author said musicians rehearse before their concerts. Actors rehearse their roles before opening of a new play. On the other hand, I find it strange. So musicians do something. On the other hand, it's strange that public speakers think they can just walk on the stage and start speaking, just like some teachers can just show up to the class and start teaching. Okay. So in my opinion, it's no less important for public speakers to rehearse their thoughts. All I'm saying is musicians rehearse regularly. On the other hand, public speakers just like that go to stage and speak. Come on, why don't they rehearse? That's what he's saying. So based on this paragraph, which of the following statements is true? We have to pick the statement that is true. Author is of the opinion that rehearsing is important for musicians, actors, and public speakers. Yeah, she says, yeah, musicians do that. Actors also do that. Of course, public speakers are supposed to be doing that. Yeah, he's of the opinion like this. I think this is a correct option. Let's also go make sure that the other options are, are not true. Author is of the opinion that rehearsing is less important for public speakers than for musicians and actors. No. He says See, musicians do that, actors do that. On the other hand, it's very strange that public speakers think they can just like that go to the stage and start speaking, right? No, he is not of that opinion. Author is of the opinion that rehearsing is more important only for musicians than public speakers. Again, yeah, we know, by now, I think we know this is not correct. Author is of the opinion that rehearsal is more important for actors than musicians. He doesn't compare actors and musicians. He says rehearsal is important for both actors and musicians. Musicians rehearse, actors rehearse, but why don't public speaker rehearse? So this is the correct option. Great. Simple text inference question. Question number 8 from KPM 2021. Again, another text inference question, I suppose. Some football players play cricket. All cricket players play hockey. Okay, oh, this is a set relation question. Okay. So among the options given below, the statement that logically follows from two statements 1 and 2. So we are given two statements. What can we deduct from it? Okay. So this is a basic set relation because some who play this or this, then all who play this. So start by using Venn diagrams to simplify, to visualize this. Things are very easy. So let's take football players. Some football players play cricket. That is, a small chunk of that is going to play cricket. So some of these football players play cricket. It means there are some players who just play cricket. Okay? So I have drawn two circle centers. All it says is we have football players and some football players play cricket. All cricket players play hockey. So all of these cricket players should be within another set of players who play hockey. Okay. So this is the set relation that we are given. Now from that we have to pick the correct option. So no football player plays hockey. Is any football player possibly can he play hockey? Yes. Right. So no football player, we know that's incorrect. And we want to also pick the statement that's logically follows. So we want to pick the correct statement. Some football players play hockey. Some football players do play hockey. This is correct. Okay. Let's just make sure the other two options are incorrect. All football players play hockey. All football players play hockey. No, there can be some football players who don't play hockey. So this is incorrect. All hockey players play football. All it says is all cricket players play hockey. All hockey players may not play football. So this is also incorrect. So the correct option here is B. Great. Let's go to the next question. Sorry about this minor disturbance. Question number 9 from KPM 2021. Okay. So this is a simple question, math question from geometry. Okay. The figure shown above PQRS is a square. The shaded portion is formed by the intersection of sectors of circles with, I'm sorry about this minor disturbance, notifications from my phone, but let's go ahead here. Shaded portion is formed by the intersection of sectors of circles. So we have a shaded portion, we can see that it's formed by sectors of circles with radius equal to the side of the square. So essentially, take circles of radius r, and then they are formed by the intersection of that. Okay. The probability that any point picked randomly within the square, so you pick a point randomly within the square, what is the probability that it falls in the shaded area? Okay, simple probability question. Essentially a question on geometry. Okay, what is this area of sectors and all that? Realize, so the required probability is area of this shaded region by the total area, right? The actual event we are interested in by all set of possible events, the ratio of that. So how do you find this area? The outer area is very simple, it's r square. But how about this this shaded area? Simple trick at this stage, questions like this, divide and conquer. Try to make shapes that you can easily write down areas for. So I'm going to make a cut like this. The moment I do that, okay, essentially now calculating, if I calculate this segment, that is P or let's also call this point O. So P O R, this small segment, it's very, very easy. Find this sectors area, subtract this triangle area, we'll get this half of the shaded region. Right? Multiply that by 2, we get the total shaded region. So So that's the problem became very, very simple by divide and conquer. So what is the sectors P or along this curve? And yes, what is area of that sector? That's very, very simple. Total area of the triangle of the circle, pi r square. That's 1/4 of the total area, right? So total circle is something like this. So it's only 1/4 of that will be this sector. So that's the area of this sector. Remove the area of this triangle from there. Okay, so that is area of this triangle is half of r times r. Okay, right triangle base times height, right? So r square by 2. And we have two such sectors. This is area of one sector. Sorry, this is area of this one segment. We have two such segments will be the area of the shaded region. So I'm going to multiply that by 2. And what we want is this ratio, right? The final answer of probabilities is ratio. So divide that by total area. That's r square. Okay, so I think the r squares cancel, and what we are left with is take this 2 inside, pi by 2 minus 1. So option C is correct. So simple geometry question, and strategy here is divide and conquer. Question number 10 from GATE BM 2021. Equilateral triangle PQR. Side PQ is divided into 4 parts. Okay, we are again looks like another geometry question. Side PQ is divided into 4 equal parts. Side QR is divided into 6 equal parts. Side PR is divided into 8 equal parts. Okay, that is a question. Length of each subdivided part is centimeter, is an integer. Okay. Okay, so let's draw the equilateral triangle. So I find it easier to visualize, with so many details. We have an equilateral triangle. It says, let's also label this PQR. PQ is divided into 4 equal parts. Okay, 4 equal parts. Then QR is divided into 6 equal parts. Okay, 6 equal parts. And then PR is divided into 8 equal parts. Okay, we'll do that. PR is divided into 8 equal parts. And it says length of each subdivided part in centimeter is an integer. So this is an integer, this is an integer, this is an integer. Right? So interestingly, okay, all the small chunks. So the small chunk is an integer, the small chunk is an integer, and of course this chunk is an integer. Minimum area of the triangle PQ possible. Okay. So this is where the bulb goes. So they say all these chunks are integers. That means the side is a multiple of 8. So that if I divide it into 8 segments, I end up with integers in centimeters. And this side, let's call it total length. That side, because it's equilateral triangle, so this side is also L, and the L is divisible by 4. And it says this L is divisible by 6. All it says is side of the equilateral triangle is divisible by 4, 6, and 8. That's a kind of equilateral triangle we are talking about, and we want the minimum area of that. Okay, now I know. So when is this area going to be minimum? We should be looking at. So the side is a multiple of 4, multiple of 6, multiple of 8, right? So what is the smallest side possible? That's a multiple of 4, 6, and 8, right? Yeah, now we know the answer. We're essentially looking for the smallest side, that is a multiple of 4, 6, and 8. We are looking for LCM of 4, 6, and 8. Okay, and at this stage, I'm going to write down the answer. So if you know how to calculate the LCM, you could do that. Or in this case, 8 is not divisible by 6. So 12 again is not divisible by 8. Then 20, no. 24. Okay, so LCM in this case is very easy. It's 24. So now the question is, what is the area of equilateral triangle of side 24? So side is 24, 24, 24. Okay, we want the area. Of course, this is also 24. And, this is 60 degrees. So half times base times height. I'll stick to that. This height is 25 cos 60, right? So half times base is 24 times height is 24 cos 60. It is root 3 by 2. So find out what this is. So this is 12. And again, this is 12. So 12 times root 3. That is 144. Option B. Another simple. Yeah, question on LCM. You have to convert the text into. You have to actually realize what they are asking for. That is, they are describing a triangle. The question essentially wants you to calculate the length of the triangle by finding LCM of 468. Once you know the length, find the area by using whichever whether you remember the formula or just use some simple base height thing to get the answer. Okay, very nice question. Great. So we are done with the 10 questions from the aptitude part of GATE BM 2021. Now I'll start with the other questions in sequence. Okay? So try the questions ahead of me, try to solve them, try to find related questions, related concepts, see where those questions showed up from the syllabus, and then try to find good references for those questions, and then try to solve them ahead of me. If you get stuck, the best way to get unstuck is to follow what I am doing. I think that's the most efficient way in which you could learn. Wish you all good luck, and I will see you with more videos. Right, in the series of videos, we are solving GATE Biomedical 2021 exam questions. We just finished the aptitude part, and here we are looking at the core biomedical part. We'll get started with one more questions. We'll go in sequence. Okay. So the first question is 1 to 17 or multiple choice questions. So essentially, you are given 4 options. You have to pick one out of those 4 options. If you pick the correct option, you get +1. In case you pick the incorrect option, you get -1 by 3. Okay. In this video, we'll solve about 4 to 5 questions and then see what's up next. First question, for f of x is some function to be a valid probability distribution function for random variable x, the value of q is. Okay, so the first question is from engineering math. We are given a function with an unknown constant, and we want to make this constant or find the value of this constant such that this function becomes a PDF. Okay, this is, I mean, essentially this constant should satisfy a very, very simple condition. When will this function be a PDF? Any function for it to be a PDF. So we know f of x, okay, from -infinity to infinity. If we integrate this, the area under this curve should be 1. So essentially, find this q such that this integral is 1. Okay, that's what the question boils down to. But the real trick here is, okay, how do you find this integral? Okay, first let's kind of like see what this integral is. I think so. This is x. This is y. It's all positive. Let's say q is positive, so it's going to be in this quadrant. And then when x is infinity, okay, denominator is too large, then this term goes to 0. And then similarly, when x is -infinity, again I think denominator is too large, so this goes to 0. So probably something like this. Okay, something like a Gaussian that goes to 0 on both the ends. So -infinity and +infinity. And the maxima is likely to happen at x is 0. Okay, and so we have to find this height of this function. Okay, let's use this condition and go ahead and find it. The only thing is, okay, how do you solve this integral? That's where the real question boils down to. Okay, this essentially, it's a probability question, but all the details are there in
definite integrals. So let me write this integral. I'm going to use all the space. So you need minus infinity to infinity. I'm going to pull up the constants out of this. Q by pi. So 1 by e power x plus e power minus x dx. Okay, so this strategy essentially boils down to recalling what kind of integral this is. Okay, so you slightly rewrite this, then I think the form becomes more evident. So this is nothing but q by pi integral minus infinity to infinity. So I'm going to take this e power x to here and here, which will be evident in a moment. Why I do that will be evident in a moment. So we have e power 2x plus 1, and then the 1 over e power x becomes e power x dx. Okay. So essentially the idea is now this is of a more recognizable form. Okay. Notice if you plug in y as e power x, okay, so dy is e power x dx, and what we have here is essentially dy by y square plus 1, which I think is a simple integrable form. So I'm going to make this conversion. How do we know that we have to plug in this thing? It's a recall based thing. It comes from practice and having sufficient practice with doing integrals and transformations. Okay, so let me do that. And this is q by pi. We'll come to the integrals in a moment. As I said, so the numerator now was just dy. The denominator became y square plus 1. Regarding the integrals, y, this thing, if x is infinity, I think y is infinity. If x is minus infinity, I think y is, this is 0, infinity, dy by y square plus 1. And you better be, at a place where you recognize what this integral is. Just q by pi tan inverse of y, and the limits are from 0 to, okay. So this is q by pi, and tan inverse infinity, I'm going to pick pi by 2, and tan inverse 0 is 0. Okay. So this is just q by 2. So this integral is q by 2, and that better be equal to 1 for this to be a probability distribution. This is 1. This implies value of q should be 2. Okay. So option A is the correct answer. This is a 1 mark engineering math question, and I would consider this question hard. It's hard because this condition is very, very, easy. As soon as you read the question, you have to use this condition. But doing this integral, you need some practice. You need to have spent some time doing this. In that sense, it's a hard question. It's a hard 1 mark question to get started with. Let's look at the next question. Okay, in the sequence, we have all the engineering math questions first. Given a scalar function b, okay, it's a 2D function, that is function of two variables, x square plus y square by 2. Directional derivative of b in the direction of the vector field. So now we are given a vector field, that is a vector which is a function of, again, x and y. Then we have given another scalar function, okay, function of x and y. This is a vector, this is a scalar. We want to find the directional derivative of v of x along the direction of this at the point 1, 1. I and j are unit vectors along the x and y directions, standard notation perspective. Okay, I think this is an easy question. So we are given b. Okay, so v is given. First step to finding directional derivative, find gradient of v. Okay, so find gradient of v. That is essentially find dou v by dou x in the I direction plus dou v by dou y j direction. So once you have the gradient, finding derivative along any direction is very, very simple. Just take this, now this is a vector. Take this and dot it with any direction, you will get the derivative along with that direction. For example, if you dot it along direction I, dou v by dou x is the derivative along the direction. If you dot it along direction j, you'll get dou v by dou y as the derivative along that direction. You could dot it along any direction, okay? And the field we are interested in is u, okay, is 3y minus 3xj. Only thing is now uh, dotting with a unit normal direction, okay, the magnitudes will not get affected. So let's convert this into a unit normal direction. That is, I want u that also has a magnitude of 1. That is very, very simple here. It's going to be, I think, y minus xj by the magnitude of this function. So x square plus y square. Where did the 3 disappear? If you take a 3 common here and there will be a 3 common here, they will get cancelled. Okay, but if you want it to be more straightforward, so this is how we end up with the unit and normal direction. So given a given gradient, directional derivative along any direction is just dot product of the unit normal and the function. What we want in this case is take grad v dotted with this unit vector u. Grad v in this case, I think, so 2xi plus 2yj by 2. So these things cancel. Essentially, so take this vector, and take dot products. Okay, so this dot u. Okay, again that's very, very simple. That's going to be xy minus xy by x square plus y square. Interestingly, this particular directional derivative is 0 along this. I know, at any point in this vector field. Usually, if it's a function of x and y, you need to further plug in this 1, 1. But it so happens that directional derivative along any point in this vector field is 0. So the answer here is 0. Okay. If this, say, numerator doesn't cancel here, you will have to evaluate this particular function at this point. But in this case, just becomes 0 by default. Okay, very, very simple question. All you need to know is what is a gradient or what is a directional derivative. That is, take gradient, dot it with a unit normal, you will get the directional derivative. Okay, 3 resistive loads are connected to ideal voltage and current sources as shown in the circuit below. The voltage VAB across the terminals A and B is equal to P. So we have given some circuit. We want to find this VA minus VB. Notice if you call this as voltage V, we essentially have one unknown variable, unknown voltage. It's a very, very simple problem to solve. And also, whenever they give currents in the network, that's going to help us, okay, because we already know one current value. And in this case, you could use Kirchhoff's first and second law, current law, voltage law, and solve this. But I think because it's a 1 mark question, this can be solved much faster. And the trick is to apply a simple source conversion, because if we know the current here in this wing, that is I30 as mentioned here, we can easily find this voltage drop. Okay, in order to find that, we can simplify this chunk over here. So I'm going to do a simple source transformation and solve this pretty fast. That is, so along these 2 points, okay, the right side of the circuit I'm going to retain as such. So there is a 20, 30, because we are interested in VA minus VB, I'm going to plug those resistors. Okay, 20 and 30 in series become 50 ohm, and then we have 24 volt, the power source over here. Now this is B, this is A. And this side of the circuit, I'm going to replace it with its Thevenin's equivalent. What we have here is a Norton equivalent. I'm going to replace that with the Thevenin's equivalent. Okay, what is Norton, what is Thevenin? Take a look at it. Okay, and we'll look at them in detail when we talk about those. Okay, so or Thevenin for this is going to be very, very simple. If it's 10 in the Norton, it's going to be 10 here. Okay, and B Thevenin is just I times R. Okay, so it's going to be 12 volts. So now this is a very, very simple problem. All we want is we have like a couple of voltage sources, we know the resistors, we find the current here, we can easily find the drop there. Okay, so let's call this current I. I is going to be very simple to find. Okay, I essentially is 12 minus 24 by 60. Okay, and I think that comes down to minus 0.2. Minus 0.2. Yeah, because I assume this direction current is actually, this is a, at a higher potential, so current is going to flow along that direction. And then VAB here is simple. VAB is just I times R. I times R, which is 50, which is 15 to 0.2. And notice it's actually a drop along this direction. So this is going to be minus 10 volts. So the correct answer is B. Okay. Notice by making this one source transformation, I solved it in 2 lines. You could do Kirchhoff laws. It's not going to be very long, but the fastest method here is what I have done here. There are many other ways to do it. There are faster ways or no equivalently fast ways. Let us know in the comments. Let's see what's up next. Fourth question in the core biomedical part. An inductor, ideal inductor with an inductance 1/3 of Henry is connected to 50 Hz sinusoidal AC voltage source. Energy stored in the inductor is 6 joules. Value of the maximum power delivered to the inductor's dashboard. Okay, this is supposed to be a 1 mark question. Okay, 1 mark question, and I would consider this question as very, very hard. I would also consider this question as very, very bad. Okay, it's a poorly framed question. We'll get to that as we solve this, but for now, let's try to solve this. So we have an AC source with just an inductor, no resistance, nothing. And some energy is given, frequency of the AC source is given. We want the power when things are maximum, or the maximum power delivered. Okay. So we have this AC circuit and inductor. So this is 50 Hz. Okay, essentially that is F. Okay, this is 50 Hz, and this is going to be 1 Hz. Now, for this circuit, we know that the voltage drop across the inductor, that could be related to this voltage V by V is minus L di by dt. Okay, that is this voltage gain here is the drop here. Let's assume a form for I, the sinusoidal form for I, and then let's see what the form for voltage is, and then we'll try to find the form for power, and from that we'll try to find maximum power. So I of t, again it's going to be sinusoidal. I'm going to write it as I naught cos omega t. Okay, so di by dt is di by dt. This is minus I naught omega sin omega t. That implies the voltage across the inductor V of t is L I naught omega sin omega t. And so if you know V of t, I of t, we can say what is P of t. Power as a function of time is V of t, I of t, and that is L I naught square omega. Okay, sin omega t cos omega t. I'm going to write that as sin 2 omega t by 2. That is using sine 2 theta formula. Okay, fine. And we know at this step things are pretty, easy. P max is just going to be the maximum value of this function, which is going to be L I naught square omega by. Okay, now omega is given, at least f is given. So omega is 2 pi f. We know omega. We know L. We do not know I, right? Or I square this thing. And that is where we need to use this piece of information. Energy stored in the inductor is 6 joules. And the reason I said this question is poorly framed or really, really bad is because at which instance is the energy stored in the inductor 6 joules? Okay. Is it during one half of the cycle? Is it during when the power is maximum? If that is the case, this is a loose sentence. I'm not really connected to this statement. Is it when the energy is maximum? None of those information is given. And so let me try to illustrate, visualize this, and say the instance that best matches the given key. Okay. So let's draw a quick time axis. Let's call this, voltage as sinusoidal. This is voltage V of t. Okay. Then the power. So notice current and voltage, or there is a phase difference between them, 90-degree phase difference. Okay, that is fine. Interestingly, power is twice the frequency of either the voltage or current. So if V of t is this, power is going to have twice the frequency. We're going to draw things out of scale. So power will have twice the frequency. So pretty much look like this. Okay. So this is P of t. Okay. And energy, we know E of t, that is just integral P dt. Okay. And what we essentially want is the maximum power here. Okay, this is P max, the magnitude of this. So this coefficient over here. And then in order to find this coefficient, the information given here is energy stored in the inductor 6 joules. By this they mean this area, that is the area under this curve till power is maximum. This E of t is 6 joules. Okay, and in order to do this real fast, you have to use one relation or recall one relation from this AC circuits. That is this area. See, notice the total area for one cycle, the power delivered is 0. Whatever you put in the inductor, you get that. So from here to here, in one full cycle, the power delivered is 0. But in half a cycle, the energy, that is the integral of the power, this area is L I naught square by 2. Okay. So for a half a cycle, it's L I naught square by 2. So what is this area? This is L I naught square by 4. So this is given to by 6 joules. So we can easily now get this term. So I'm going to write this in terms of this as well as the omega. So this is L I naught square by 4. So into 2 omega. Omega is 2 pi f, that is 4 pi f. Okay. So this term is given to be 6 joules. So this is 6 into 4 into pi into frequency is 50. So quickly calculate that one. That comes down to 1200 pi, which is the official answer. Notice the statement is very, very loose and it's not clear whether they are referring to energy at this point. If that is the case, see, what I would have done is the value of the maximum power delivered to the inductor is dash watts. The energy stored in inductor at that point is 6 joules. At that instance is 60 joules. Or then the energy stored in the inductor is 6 joules. I would have used a connecting word to say that, to be very, very clear on what they mean by the energy stored. Okay, it could mean this full cycle, half cycle, or energy stored is maximum, right? It's not clear. In that sense, I would consider this is framed very poorly. And for a 1 mark, I would say this is a very hard question. It does involve some recall-based things. And of course, as a take-home, try to derive all these expressions. You know the expression for P of t, so try to integrate it for half a cycle and make sure you get L I naught square by 2. So interestingly, this is what you would get in a DC circuit, Li square by 2. Even for a AC circuit, half of the cycle, the energy stored in an inductor is L I naught square by 2. So using P of t, do this integral for half a cycle and try to verify that. And then let's see what's up next. Okay, Fourier transform x of j omega is this, then we have to find this. So, okay, this is a standard question that shows up pretty much every year. The trick is to use some properties of Fourier transform and inverse Fourier transform. Basically, those related to scaling and shifting. And they have also given this, very, very important sinc function over here. Try this question, and I'll upload the answer by tonight, or maximum, latest by tomorrow. Let x of j omega denote the Fourier transform of x of t. X of j omega is the sinc function. Then 1 by 2 pi x of j omega d omega is dash. This kind of question is very, very typical in the GATE exam. This is from Signals and Systems. First thing is to notice what this integral is. It's a specific version of the inverse Fourier transform. And the function we are talking about is the sinc function. And there is some, by the exponential here, we know there is some scaling and shifting involved here. So if you know the standard Fourier transform for the sinc function, okay, as well as the inverse Fourier transform, then a couple of properties on scaling and shifting, and the definition of inverse Fourier transform, you should be able to solve this very, very easily. I'm going to do that here, write down all the properties as well as explain how to solve this very fast. So we have a function x of t, and if we take Fourier transform, okay, we get x of j omega. From the time domain, we go to the frequency domain, and this forward arrow is the Fourier transform that you know. If we take x of j omega, we do the inverse Fourier transform, we get back x of t. Right? First thing is, let's write down what is this inverse Fourier transform. So we get back the function x of t if we do 1 by 2 pi minus infinity to infinity Fourier transform of a function e power j omega t dt. Okay. So this is the definition of how to take an inverse Fourier transform. Notice this particular integral, we'll get this. When can we get rid of this particular term from this integral? When t is equal to 0. That is, for x of 0 is essentially 1 by 2 pi minus infinity to infinity x of j omega d omega. Sorry, the integral over here is respect to omega. J omega d omega. Okay. So all they are asking is, so we have this inverse Fourier transform of a function x of t. Now find what is x of 0. That's all they want. Okay, and recognize this particular function is a sinc function. Okay, so first thing, sine pi f by pi f. I'm going to write this as sinc of f. Is now the sinc function. It's one of the most important functions. And let's look at the Fourier transform of this. So this is where we need to know what are the Fourier transform and inverse Fourier transform of the sinc function. Okay, essentially sinc function is a Fourier transform of a rectangular function. That is, take a rect of t by tau. We'll explain what this a and tau. Essentially, we have a function of time with parameters a and tau. If you take Fourier transform of that, you get the sinc function. A tau sinc of f tau. And of course, now if you take this particular function and take inverse Fourier transform, you get back this function. This function is just, rectangle function. That is, it has an amplitude of A. Okay, it's essentially a window function. It has an amplitude of A. Okay, this axis is time, and it's non-zero from minus tau by 2 to tau by 2. This is the rect function. Okay, so this function over here is A rect of t by tau. Okay, so you take this function, you take Fourier transform, you get back a sinc function. Interestingly, notice this function has specific parameters. A is 10 and tau is essentially 1. Okay. Okay. With this, can we take the inverse Fourier transform of this particular function? So find x of 0? Not really. We also have this interesting term over here, okay, which is where we are going to use one more property of Fourier transform. Okay. So x of t minus a. Say x of t becomes x of j omega. What does x of t minus a shifted version of x of t becomes? Interestingly, this is just e power minus j omega a x of j omega. That is, you take the original Fourier transform, multiply that by e power j omega a, get the Fourier transform of this shifted function. Interestingly, what we have here is the Fourier transform. Now, if you do inverse Fourier transform, what you are going to get is this rectangular function shifted by a factor over here. Okay, so essentially, what we have here is the Fourier transform has this particular term. What it means is that this function is going to have a shifting. That is, the rectangular function is going to be shifted slightly. Okay, so using this, we know what we are looking for is x of 0, and to find that, we are essentially going to use these two properties. So what we have here is essentially, we know 10 rect of t, that is a is 10, tau is 1. This is Fourier transform of 10 sinc of f. Okay, this means 10 e power minus j omega. I'm going to write this as 2 pi f and divided by 2, so that we have j into pi f, this factor over here, times sinc f. Okay, if you take inverse Fourier transform of this, what we will end up with is essentially 10 rect of t minus half. That is, take the rectangular function with tau is 1, so this point is 0.5, shifted, you get back this function. And what is the value of that function, shifted function, at x of 0? Notice all the options are non-zero. So we are shifting such that the function still remains non-zero at the origin. Okay, and the value of that function, this function shifted, non-zero value will still be this a, which is this coefficient over here. So the option here is C, is the correct answer. Okay, this looks slightly complicated, but it becomes easier and easier once you know what Fourier transform is, what inverse Fourier transform is. First thing to recognize that we are asking for x of 0. That's the first detail. And based on this particular function, so Fourier transform is sinc function. So we know the actual function is rectangular function. And to account for this e power j omega or j pi f term, we essentially use one more property. That is, we take the function shifted, then take Fourier transform, we get this additional function. Okay, so using 1, 2, and 3, we get the answer as 10 in like 2 steps. That is, if it were 10 sinc f, if you do inverse Fourier transform, we get 10 rectangle of t. What we have is this function, 10 e power j pi f sinc f. Okay, if you take inverse Fourier transform, that you will get 10 rect t minus half. That is the rectangular shifted by 0.5. And notice all the answers are non-zero. So the shifted value will have an amplitude of 10. Okay. Question number 6 from GATE Biomedical 2021. Okay, this is a one more question. We are we are given a seemingly complicated combinatorial circuit, and then so the outputs are y1, y0. Okay, it's a 2-bit output, and we are given 4 inputs: a0, a1, b0, b1. Question is, what is the maximum value of y? That is, 16 combinations are possible over here. Out of those combinations, when will we get the maximum here? Or in fact, we are interested in the maximum value. We are not really interested in what the inputs are. We are just interested in what will be the maximum of this. Whether y1 can be 1, y0 can be 1. In that case, maximum will be 11. Whether it's possible, or the maximum possible here is one of these values. Okay? So there are 2 ways, of course, to solve this problem. We can try 16 combinations of inputs and see which maximum we get. What is the maximum we get? Or 16 combinations is a lot for a 1 mark problem. Start with the output, see if this is possible, and then if this is not possible, see if this is possible, and then go on. Try to check the 4 options in this order, so that we start with the maximum possible, check feasibility, then move on to the lower ones. Let me show an example. Okay, and before we do that, let's also make sure we know what all these gates are. We have an OR gate here, we have an XOR gate here, and then we have an AND gate here. This is XOR and AND. Okay, so we have only 3 types of gates here. So OR gate, I think we all know, it's 0, 0, 0, 1, 1, 0, 1, 1. These are the possible inputs, 2 input terminals. Outputs could be 0, 1, 1, 1. And for an AND gate, again, I think we know inputs could be 0, 0, 0, 1, 1, 0, 1, 1. Output will be 0, 0, 0, 1. For an XOR gate, okay, inputs could be 0, 0, 0, 1, 1, 0, 1, 1. The outputs will be 1 when the inputs are different. So this is 1, 1, 0, 0. With this, I'm going to start with this highest possible value. That is, first I'm going to ask if 1, 1 is possible. Let's say the outputs here are 1, 1. Let's see if any allowable inputs result in this output. Okay. For y1 to be 1, we know both the inputs should be 1 and 1. So this has to be 1 and this has to be 1, which means that okay, the input here is 1 and the input here is also 1. This means that if 1 and 1 are the inputs here, we cannot get an output 1 in an XOR gate. So in this case, if 1 is here, 1 here is not possible. So this option is ruled out just by checking here. So next, what I'm going to do is to check if this is possible. That is, 0 here is possible. Okay, if this is a 1 here, okay, these 2 inputs better be 1. Okay, and if these 2 inputs are 1, can we get a 0? No. Again, we can rule out 10 because for this to be 1, these 2 needs to be 1. If these 2 are 1, the output here should be a 0. Okay, this is possible at this stage. Okay, but just backtrack a little further and see if this is not possible. Okay, so we have 1 here and we have 1 here, which means we have 1 and 1 and 1 here. Okay, which means we have 1 here and 1 here. So interestingly, the inputs to this NOR gate are 1 and 1, and the output here at this point has to be 1, right? If inputs are 1 and 1, the output has to be a 0. So that is not possible. For that reason, okay, we have inconsistency, which means this output is not possible. So y10, y00 is not possible. I'm going to rule that out. So next I'm going to try a lower value, which is 0, 1. Okay, if that is feasible, then that is a maximum value of y that's possible. So is this possible? So this is going to be a 0 here and 1 here. Let's again backtrack and see if that is feasible. If this is 0 here, many combinations are possible. To keep things simple, I'm just going to assume that this is 0 and this is 1. What we have here is 0 and 1. Okay? Let's backtrack and see if this is this is fine. So 0 and 1 we have a 0, 0 and 1 we have a 1. So an XOR gate, that is fine. So now we have a 1 here, which means this is 1, this is 1. We have a 0 here because this input is 1. It means this input better be 0. So this is 0, okay, and the output here is 0. And interestingly, now if this input is 1, okay, input here is 1, input here is 0, and through an XOR gate we get a 1 here. That is fine. Can we somehow get 1 here through an OR gate for any combination of A0 and A1? Yes, that's possible. In fact, 3 combinations can give this 1. So this is possible. Let's say this is just 1, 1. Can we get a 0 here through an OR gate? Again, that's possible, right? Let's say this is 0, 0. So starting with this input, this is possible. Okay, we can consistently get this value. So the maximum value of y here is option A. Okay, because we have been like that, starting with the highest value. This was not feasible. This was not feasible. Our answer here is 0. If this were inconsistent, just like these 2 cases, then 0, 0 would have been the answer.
Question number 7 in GATE BM 2021. The block diagram shown below an analog signal, okay, it's sinusoidal. It's quantized into a 10-bit Nyquist ADC. Later, 4 LSBs are dropped and 6 MSBs are converted to an analog signal. Okay, so we start with an analog signal. There is 10-bit quantization, 4 bits are dropped, then 6 bits are converted back to analog. Assume uniform distribution of the quantization noise. The peak SQNR at the output of DAC is dash decibels. So we want the signal to quantization noise ratio at this thing. Okay, first thing, notice this is a 1 mark question. Okay, so you don't have to really overthink about this thing. And this uses an obscure result. Okay, if you know digital signal processing, is a very well known result. Okay, I have given the references below. If you are not that familiar with discrete signal processing, or sorry, digital signal processing, this uses an obscure result, okay, due to Bennett from 1940s or 50s. Okay, I'm just going to write that result over here. I have given references below. You could read how you get that particular result I am going to write. Okay, the SQNR. So whenever you have a continuous signal, you quantize that, and under certain conditions, okay, within the Nyquist limit, things are sinusoidal, and we have like uniform distribution of quantization noise. All those cases, this SQNR in decibels, okay, this is going to be 1.7 plus 6.02 times Q decibels. That is, if Q bits are used, the quantization uses Q bits, quantization of an analog signal uses Q bits, the signal to quantization noise ratio is going to be this. Given this, again, this is a typical gate way of framing. Now, if you do all these things, what is going to be the quantization noise ratio? That is, you have to use this formula, but what is the value of Q that you are going to use? Okay, so I think this option corresponds to Q is 10, okay, roughly 6 times 10, 60 plus 1.7, and this option corresponds to Q is I think 8. Okay, this option corresponds to Q is 4, and this option corresponds to Q is 6. Okay, when you do this kind of processing, either that's depicted in the figure or described in this text, which is the appropriate Q you should use for this question. Okay, specifically with this kind of processing, what is the highest Q you are supposed to be using? That's what they are asking. Okay, so you start with 10-bit quantization and you drop off 4 least significant bits. That means at the end of it, you do 6-bit quantization. Either try to get it from the figure or try to get it from the text. Okay, this essentially says you are doing a 6-bit quantization. That is the value of Q you are supposed to be using is 6. If you do that, Q is 6, you get SQNR close to 37.88. Okay, it's a recall based question.
it's kind of obscure if you don't know digital signal processing. I have given the references below to know more about this. But the real trick here is either you have to infer what is the correct value of Q that you should be using from the text here or from the depiction here. The correct value is 6, and that should give a peak SQNR of 37.88 decibels. Question number 8 from GATE Biomedical 2021. For a linear stable second order system, if the unit step response is such that the peak time is twice the rise time, then the system is. Okay. This is a question from control systems. Interestingly, so in the syllabus it mentioned only basics of transfer function is there in control systems. So they started asking questions from time response of second order systems and all that. So I suppose by transfer function they mean pretty much everything in control systems. Okay. So this particular question essentially, okay, second order control system is linear, stable, and okay, for a unit step response, peak time is twice the rise time. So condition relating peak time and rise time is given. You want to say whether it's underdamped, undamped, overdamped, or critically damped. First thing is, I think this notion of peak time is not well defined for a overdamped system. So let's rule this out. What I am going to do is, so there are expressions for peak time, rise time, and a couple of other things defined for an undamped system. I'm going to start using those expressions and see where the given conditions lead us. Okay, a good reference for this is Norman Nice. There are many good control system books that are very useful for GATE, Wagata, Kruo, or even Nagratan Gopal. But after going through many of them, the book that I'm starting to prescribe is this one by Norman Nice. And this has a, I think in the 4th chapter, the second order system is described in detail. Take a look at that for involving theory. But for today, I'm going to just write down the expressions for peak time, rise time, and then see whether we get A, B, or B. I'm going to give a very, very brief intro over here. Let's say we have a second order system, and let's plot the roots of the denominator for the second order system. Okay, and essentially we are plotting the poles. So this is the S plane. Okay, so we have the real axis over here and the imaginary axis over here. And let's say we have a complex repeating pole or complex conjugate poles. Okay, so we have a pole here and a pole here. Let's say the two poles of the system are 1 and 2, which are minus omega n zeta. Omega n is known as the natural frequency and zeta is known as the damping ratio. And then we have plus or minus j omega n root of square minus 1. So we'll start with an underdamped case, that is 0 less than zeta less than 1. Okay, and if we draw these two poles over here, so the real part is going to be minus omega n zeta. This is also known as exponential damping frequency. And the imaginary part is plus or minus j omega n root of sigma square minus 1. Given the two poles of an underdamped system, okay, so the poles are over here and here, and so based on these parameters, essentially the natural frequency and the damping ratio, let's see what this peak time and rise time are. Peak time is essentially pi by this damp frequency, that is omega n root of zeta square minus 1. Okay, and that is equal to twice the rise time. Okay, and rise time is again PR is pi minus theta by omega n root of zeta square minus 1. Okay, and so this is TR, so we have pi TR. This is a condition given in the question, and this theta over here is essentially the angle that the poles form here. Okay, interestingly, so these two terms are common, they cancel. we can actually find theta from the given relation. So this relation implies that pi is 2 pi minus 2 theta. This implies theta is pi over 2. So interestingly, it says this angle of this pole is such that it's 90 degrees, which means these two poles lie in the imaginary axis. That is, the real part is totally 0. So the poles are somewhere over here. And when the poles are such that they lie in the imaginary axis and there is no real part, we are actually talking about an undamped case. Had it been theta is actually some value between 0 and 90 degrees, like shown in this figure, then our underdamped assumption holds good. But in this case, we have a 90 degree. And if theta were such that theta is 0 degree, we would have been actually looking at a case that is critically damped. So we started off with this underdamped assumption, and for that, theta would be between 0 and pi by 2. Interestingly, in this case, theta is pi by 2, okay, which means we are talking about an undamped case. Had theta been 0 degrees, we would actually be referring to a critically damped case. Again, for more details and basic theory, I suggest you take a look at 4th chapter in normal maths. Question number 9 from GATE Biomedical 2021. Which of the following displacement sensors is known to have a high sensitivity and a relatively large measurement range? Okay, so we are talking about a displacement sensors, strain gauge, capacity sensor, lubricity, piezoelectric sensors, and we want a sensor with a high sensitivity and relatively larger measurement range. Okay, this is one thing. When the measurement range is very, very large, the sensor that actually best matches is LVDT. Okay. Piezo, capacitive, and strains usually work with small measurement range. Okay. But the moment we say it's a large measurement range, the answer is LVDT. And it would be a good idea to go check the properties of the other 3 displacement sensors. Okay, how about the sensitivity of each of these sensors, and again, what is the typical measurement range for these sensors, which could be typical GATE questions in future biomedical exams. Question number 10 from GATE Biomedical 2021. Which of the following temperature sensors is used in contact type digital thermometers for measuring body temperature? So we want contact type digital thermometer for measuring body temperature. It's an interesting question. Okay, infrared LED photo detector pair is likely to be used in non-contact type body temperature measurement. Or a similar setup is also there in pulse oximeters, but this is non-contact type body temperature. So it's between thermocouple, thermistor, and RTDs. Okay. Interestingly, you could go try to find any temperature sensor in biomedical application that either uses a thermocouple or an RTD. There is none other than thermistors. So among these 3, although all 3, thermocouple, thermistor, RTD, could be used for temperature measurement, the sensor that is cost effective, that works well in the human body temperature range, biomedical temperature range, okay, and that is accurate and sensitive enough is a thermistor. Thermocouples and RTDs have applications elsewhere, in industrial applications and all that. But as far as biomedical is concerned, the sensors that best suit us are thermistor. If you are so curious, you can go try to find a sensor that's either a thermocouple or a RTD that is being used in a biomedical application. I don't think you will find one. If you find one, leave a note in the comment section and we'll take a further look at it. Question number 11 from GATE Biomedical 2021. The pH of blood in a healthy human is precisely in the range of... Okay, we know this is slightly alkaline. This is a memory-based question. It's slightly alkaline. This one is pretty much neutral. It's between either this, or this. And it's a recall-based question. The correct answer is from 7.35 to 7.45. Okay. Now, of course, you could go check about pH of other bodily fluids, like what is the pH of acid in the stomach, things like that. Question number 12 from Gate Biomedical 2021. Which of the following is a cranial bone in the human body? Okay, essentially a bone that is there in the top part of the skull. Occipital, it is there in the top part of the skull. So this is correct. Let's just go make sure that the other options are not correct. Mandible is the jaw. Okay, so this is not correct. Cockeye this is the tailbone, or the bottom part of the spinal cord. Again, this is not the case. Sternum is there in the chest over here. Again, this is not the answer. Correct answer is occipital. Mandible, you might think it's there in the skull, but actually the cranial bone, only occipital is there. Question number 13 from Gate Biomedical 2021. Which of the following glands produces a thyroid stimulating hormone? Okay, we have TSH. Thyroid, okay, typically we have T3, T4, perhaps calcitonin, that. Parathyroid, what I could recall as parathyroid hormone. Okay, again, TSH is not from here. Pituitary, we have thyroid stimulating hormone and the growth hormone. So TSH is produced by the pituitary gland. And pineal, I think the well-known hormone is melatonin. Okay. So the correct answer here is option C. Question number 14 from Gate Biomedical 2021. Which of the following causes myocardial infarction? Obstruction in one of the arteries supplying blood to the heart, obstruction in one of the arteries supplying blood to the brain, one of the veins draining blood from the heart, one of the veins draining blood from the brain. Interestingly, myocardial infarction essentially is heart attack, and myocardium refers to the heart. So it's either this or this. We can rule out supplying to the brain. This is what happens in case of stroke. Okay. So whether it's the artery, obstruction of the artery, or obstruction of the veins. Let's say we have the aorta over here, and we have like the three main arteries from it: RCA, LCX, and LAD. One of these major arteries, coronary arteries, get blocked. Okay, that is known as a myocardial infarction. So one of the arteries supplying blood to the heart, this gets blocked. That is myocardial infarction. And as far as the vein system goes, okay, this is a tree-like structure, artery. Veins doesn't have a tree-like structure similar to the arteries. Okay, so even if one part in a vein is blocked, blood can easily take a different route. Okay, towards the lung for oxygenation, or wherever it's going. So vein is not a tree. If one path is blocked, easily it can find a different path. So that's why obstruction of one of the arteries is a major issue. It's a myocardial infarction. Question number 15 from Gate Biomedical 2021. If we consider blood as a suspension of RBCs in a Newtonian fluid, the shear forces experienced by the RBCs during blood flow would dash randomized orientation of blood cells, align RBCs along long axis, align RBCs along short axis, create an equal distribution of RBCs. Okay. So we have a blood vessel, and as things flow, what would happen to the RBCs? RBCs are highly deformable. Okay, and to make this flow very, very efficient, what they are going to do is to start aligning along the direction of the flow. Okay, that is, it will start aligning along the direction of velocity vectors, which is a streamline, essentially tangents to the velocity vector. Okay, so the RBC, which is normally like this. Okay, and if you look at its cross section, it will be something like this. So we have the short axis and the long axis. The RBC is going to align more and more along with the flow. Just think of a shape of a fish. Okay. So that the option that best makes sense here is option B. That is, the RBCs will align along their own axis with streamlines. Question number 16 from Gate Biomedical 2021. As shown in the figure, the water contact angles of surfaces A and B, or theta A. Okay, we have surface A, surface B, and we have water contact angle to be theta A here and theta B here. Based on the figure, which of the following statements is given below is true? Okay. Surface A is hydrophilic, hydrophobic. Okay, so based on this angle, we have to specify whether this is hydrophilic and hydrophobic. This is more like a leaf of a lily plant. The leaf surface doesn't easily get wet due to water. This is an example of an hydrophobic phobic, that is water and the surface doesn't interact well. Okay? And of course, this is kind of the opposite of this, where the water droplet will pretty much interact well with the surface. So this is an example of a hydrophilic surface. Okay, so surface A is hydrophilic and surface B is hydrophobic. Yeah, this is correct. And of course, this is incorrect. Both surfaces are hydrophilic, both surfaces are hydrophobic. All these are incorrect. Okay, so this is a question from biomaterials, very, very basic question. Just by knowing what philic and phobic is, we can actually answer this. Question number 17 from GATE Biomedical 2021. Okay, another theory question from anatomy. Which of the following is a bone resorbing cell? Okay, we have osteoblasts, osteoclasts, osteocytes, and osteocalcin. Okay, the moment we have osteo, we know all of them refers to bone, but what we want is a bone resorbing cell. Blast, blastoma, blast, these refer to cells that form bones. Okay, so bone forming. Osteoclasts, on the other hand, are bone resorbing. So the correct option here is option B. And osteocytes, these are just bone cells. And osteocalcin, this essentially refers to, these are proteins in the bone. So bone resorbing cells or osteoclasts. Questions 18 to 20 or multiple select questions. That is, 4 options are given. Out of this 4 options, one or more than one option could be correct. Okay. So if you pick all the options that are correct, you get 1 mark. If you pick incorrect options or if you leave out a correct option, you don't get negative marks. So these are questions that I would certainly suggest that you attempt all MSQs, because there is no negative marks. Even if you don't know that, just listen. Question number 18 from GATE Biomedical 2021. Which of the following statements are correct in the context of planar X-ray imaging? Using fast X-ray strains, improve spatial resolution. Using fast X-ray strain, worsen spatial resolution. Decreasing tube current decreases signal to noise SNR. Decreases tube current decreases SNR. Okay, so first thing is, using fast X-ray strain, does it improve spatial resolution or worsen spatial resolution? Okay, fast X-ray strain, a good analogy is like this, taking photos at night. Will that give better resolution images or lower resolution images? They are going to give lower resolution images. In fact, any component, most components that you would use in an optical system will worsen spatial resolution. And this case, B is the correct option. And decreasing tube current decreases signal SNR. Okay, so tube current refers to this, flow of electrons from cathode to anode in X-ray generation. And if tube current is less, X-rays will be lesser, so signal will be lesser. So decreasing tube current will decrease signal to noise ratio. On the other hand, if you increase tube current, there will be more X-rays, the signal will be higher. Okay? So the correct options here are B and C. Question number 19 from GATE Biomedical 2021 looks like another anatomy and physiology question, or you could say this is from biomechanics. While comparing parallel fiber and pinnate muscles of a given volume, which of the following statements are true? So we are comparing parallel fibers and pinnate muscles. Okay, so these are essentially two muscular architectures. So let's say we have a tendon. Parallel fibers are going to be like this. Okay. So we have the tendon over here, and then the connecting muscles will have a structure like this. So this is parallel, and pinnate, one way to draw them would be, let's say we have the connecting tissues over here, and the muscles are connected at an oblique angle. That is, say pinnate muscle fibers are oriented at an angle to the actual connecting tendons. Okay? So these are pinnate. Notice in this case the cross-sectional area is very small, so they will generate a smaller force. Okay, so parallel fibers provide more muscular force. This is actually not correct. Okay, on the other hand, the cross-sectional area of this is very high, so pinnate fibers, pinnate muscles will actually provide more muscular force. And again, the fibers are oriented along this direction, they can change their length very easily compared to this oblique orientation, so they can facilitate better shortening. So parallel fibers facilitate better shortening, this is correct. Pinnate fibers on the other hand, they cannot, even they shorten because it's at an oblique angle, the net effect will be very less. So I think options A and D are correct. Question number 20 from GATE Biomedical 2021. Which of the following may cause failure of bone implants? This question is from Biomaterials. Okay, essentially we have given 4 processes and also defined the processes. Okay, corresponding definitions hopefully, and we have to pick those one which cause failure. Okay, stress shielding, reduction of bone density due to removal of typical stress from bone by an implant. When you put an implant, that is going to lower the load on the bone, that will actually make the bone density lower. Okay, the bone that is not in use, that will become smaller and smaller, or density will become smaller and smaller. As the bone becomes smaller, it will fail. So this is the correct option. Aseptic loosening. Aseptic is without infection, but the thing loosens. Loss of bond between bone and implant, the absence of an infection. Yes, although there is no infection, the moment this bond loosens, it can lead to mechanical failure. Okay, so this is also a cause of failure in bone implants. This option is correct. Fretting fatigue, progressive deterioration of material by small scale rubbing. As the bone and implants keep on rubbing, okay, there's this chance of deterioration of material that's known as fretting fatigue. It's more and more material deteriorates, the implant fails more and more. So again, this is the correct option. Osseointegration, formation of a direct interface between an implant and a bone without intervening soft tissues. In many cases, when we put an implant, we want the implant to form a nice interface between that and the bone, so that the implant gels well with the surrounding medium or integrates well with the surrounding medium. This is a feature that we want in implants. It's not a failure. This is something that we want. So this is not a failure. So options A, B, C are correct. Question number 21 to 25, numerical answer type, 1 mark question. Okay, so we are getting to question number 21, and the following 5 questions are NAT type. That means there will be a blank which needs to be filled up with a numerical value. Again, these questions carry no negative marks, so I strongly suggest that you answer all of them.
Hello, in this series of videos, we discuss solutions for the GATE Biomedical 2021 paper. And we are going in sequence. Currently, we are at question number 21. And we are starting with numerical answer type questions. Okay? So all these questions have a blank, and we have to fill the blank with a numerical value. That's some number, integer, or a decimal. Okay, and these questions, if you fill up the right number, usually within a specific range, you get 1 mark. The number you enter here is not within the range of official answer key. Okay, you get 0 marks. There are no negative marks here. So one tip here is, whether you know the question, whether you know the answer, whether you understand the question, whatever it is, at the last 5 minutes of the examination, fill up all numerical value type, numerical answer type questions with some number, say 0 or 1 or something like that. Okay. There are no negative marks while you did that. Okay. With that, let's get started with question number 21. The minimum value of min of the function given below is dash, rounded off to the nearest integer. Your multivariable function is given. Notice this is most powers of 2, so it's quadratic. We want to know the minimum of this. Okay, multivariable calculus, almost similar to single variable calculus. We have to make sure that derivatives are 0. In this case, the gradient is 0. Okay. So the gradient is 0 for it to be an extremum point. Notice there are no limits on the variables. Suppose they vary from infinity to minus infinity, and because this is a quadratic function, there is going to be one minimum or maximum. So the gradient is going to be a vector, and this will be dou f by dou x1. We call it vector I direction, or I'm going to call it E1 direction, okay, plus dou f by dou x2. Similarly, j direction, or I'm going to refer this as E2 direction. It's a unit vector along, say, j direction. Plus dou f by dou x3 and E3 vector. This is a gradient, and these are partial derivatives. Notice this is a vector, so we have like 3 terms here. Okay? So let's calculate this term. If you take partial derivative of this with respect to x1, you get 2x1 and a half here, so you get x1 here and you get 2 here. So this is x1 minus 2 in the E1 direction, plus similarly symmetric, so x2 minus 2 in the E2 direction, and x3 minus 2 in the E3 direction. Great. Now, because this vector is 0, all these terms are 0, so this is 0, this is 0, and this is 0. And so the point we are interested in is 2, 2, 2. Okay? And with this, the function value was, this is half of 2 square plus 2 square plus 2 square, that is 12, minus 2 times 2 plus 2 plus 2, that is 6. So this is 6 minus 12, which is minus 6. Okay? First thing, so there is only one solution here, so this has to be a minimum. Or to just make sure this is a minimum and not a maximum, you could quickly estimate this function at a different value. For example, what is f of 0, 0, 0? This value is higher than this, then this point is a minimum. This value is the minimum value. This value turns out to be smaller than this, then this point is likely to be a maximum. F of 0, 0, 0 is 0, so which is greater than minus 6, which means this point is actually a minimum. A better way to do that is using Hessian's and the second derivative test. But for a gate level question, you don't need that much information. Okay, very, very simple 2 marks, and we'll go to the next one. Question number 22 from GATE Biomedical 2021. A continuous time transfer function h of s. This function is converted to a discrete time transfer function h of z using a bilinear transform, 100 megahertz sampling rate. The pole of h of z is located at c. Okay. So you are given a transfer function for a continuous system, and you have to convert this into a transfer function for a discrete time system, that is h of z. And this transformation is known as a bilinear transform. This transformation happens at a specific sampling rate. Okay, let's call this f. And we want the pole of this h of z, that is, we want to find the roots of the denominator of h of z. So the question really boils down to how we go from h of s to h of z, and that boils down to the definition of what a bilinear transformation is. Essentially, h of z, this bilinear transformation, is take h of s and substitute s as 2 by t into z minus 1 by z plus 1. Notice, so wherever you have s, substitute this expression here, okay, to make it a function of z. And this t is essentially 1 over f, which is the sampling period. So this information is essentially given in the question. Okay, let's go ahead and plug this expression here in this transfer function. Let's see what we get. So we have 1 plus, so we have 1 by 10 to 6 term here. And this s is essentially 2 by t into z minus 1 by z plus 1. And then there is also the s in the denominator. So this is 2 by t into z minus 1 by z plus 1. So take this to the numerator, and we quickly get t by 2 into z plus 1 by z minus 1, okay, plus 1 over 10 power 6. These two terms cancel. And to actually get a numerator and a denominator, I'm going to write this as you know, 10 power 6 t into z plus 1 plus 2 into z minus 1. So that's a numerator. And the denominator we have as 2 into z minus 1 into 10 power 6. So we want the roots of the denominator, which is when will this term become 0? When z is 1. So the answer here is z is 1. Very, very simple question, just that this bilinear transformation is somewhat of an obscure transformation. This is from signals and systems, and very rarely one comes across a question using this transformation. So if you know what to substitute for yes, get the answer just like that. If you don't know that, okay, it's an NAT, just guess some number, 0 or 1. In this case, you might actually get marks for. Okay. Question number 23. Consider a type 2 unity feedback system, intersection of the initial minus 40 decibel per decade segment of its Bode plot with a 0 dB line occurs at a frequency of 2 radians per second. Acceleration error function of the system KAS. Okay. So we are given some information from the Bode plot, and we want to know what this acceleration error constant is. Okay, I'm going to make this video really brief, so I'm not going to go into a lot of details on what a type 2 system is, what is an acceleration error constant, what a Bode plot, and how in that Bode plot you can find this K, but I'll give some very, very brief minimal information. Okay, and if you need more information, I suggest you look at Norman Nice, okay, control system book, and chapter specific to frequency response. Okay, so it's a question from control systems, specifically frequency response. So quickly, okay. So Bode plot, you have you plot this decibels. So 20 log of this transfer function. We're going to call that magnitude of the transfer function as m. Have it in this axis, then you have omega in this axis. Okay. So for a type 2, type 1, type 0 system, so the G of S will usually look something like, there will be some terms in the numerator, then there will be some terms in the denominator, let's say S plus Zi, and perhaps product of these terms, okay, and then similarly product of poles in the denominator, okay, and then there could be some poles that are 0, that is some S power m term here. Okay, the value of this m determines what kind of a system it is. Okay, so here we have m and here we have type. Okay, m is 0, it's type 0. If m is 1, it's type 1. If m is 2, it's type 2 system. So in this case, what it says is we have a type 2 unity feedback system, and so essentially we are looking at this. The reason this matters is a type 0 system will have a constant line like this, and from that you can easily find what is Kp. Okay, so from this it's easy to find the position error constant Kp. Okay, from a type 0 system. From a type 1 system, it's easy to find the velocity error constant. From type 2 system, it's very easy to find the acceleration error constant. I'm just going to focus on this bit over here. For a type 2 system, the Bode plot will start from some point over here, and then initial drop will be minus 40 dB per decade. Okay. After some time, based on the zeros and poles here, this can actually take multiple paths. Okay. The plot could look like this, in many ways. Let's say the graph looks like this. But in order to find Ka, if we were to extend this initial straight line, okay, this will touch somewhere over here at some omega, right? Let's call it omega A. This frequency value at essentially 0 decibels, okay? This omega A will be equal to square root of Ka, that is square root of this acceleration error function. This omega A is given, So we know 2 is square root of Ka, which implies Ka is just square of 2, which is 4. So I skipped a lot of details over here. So, okay, why does a Bode plot look like this? Initially has this minus 40 decibel per decade. What is the Bode plot? What is a type 2 system? And why does this particular value here, value of omega 0 decibels is root Ka and all that? Yeah, I intentionally wanted to keep this video very short. We'll discuss that in a future video. But for now, if you are very curious, I suggest you look at chapters on frequency response from normal noise. Okay. Great. Question number 24. The radioactivity of a radionuclide with decay constant, okay, something. Second inverse is 6 millicurie at 10:30 a.m. Radioactivity of the radionuclide at 4:30 p.m. on the same day will be dash millicurie. So a couple of things. So in GATE, it's very typical to have exponential fit problems, okay? Some kind of exponential decay, rise, growth, something like that. It's very, very typical. 1 or 2 questions will be there. If it's a 2 mark, they will ask you to find an exponential parameter that is solve an inverse problem. In this case, I think this is on 1 mark. So it's a direct exponential problem. The parameters are given. You have to find the value of the exponential function at a different time. Okay. There are a couple of details here. We'll get to that. Essentially, it says you start with some amount of radioactivity. This radioactivity, initial activity, is going to decay. That is exponentially decay with the rate constant of lambda. And the amount of decay depends on the time that has evolved. Okay. It's just an exponential function. And this will give the new radioactivity. That is radioactivity at a time t. Okay. And so this decay constant is essentially lambda. The time evolved is given between 10:30 to 4:30 on the same day. And the initial value is also given. This is 6 millicurie. Ci stands for curie. It's a unit for radioactivity. And it's essentially says there are like, I think, 3.7 into 10 power 10 decays per second. So we have decays per second. Okay. And also 1 decay per second, it's also known as 1 becquerel, but that's for a different day. Perhaps it might show up in the mock test. But for now, just realize that Curie says how many nuclei decays per second. Okay. So initial is given, time evolved is given, this constant is given. All you have to find is its value at a different time. How much time does it evolve? So 10:30, 11:30, 12:30, 1:30, 2:30, 3:30, 4:30. So that is 6 hours, right? So the new n will be given by, take the initial n, that is 6. We want the final answer in millicurie. So keep 6 as such, 6 millicurie. And this is e raised to the power of 3.22 into 10 power minus 5 times time is 6 hours. And because this is in seconds, let's also convert this into seconds. So this is 3600. Quickly calculate this one. I get 2.99. So rounded off to 2 decimal places, I get 2.9. Right? So very, very simple question. And this also, I think we are starting to get questions from medical imaging. Very, very basic question. And remember, such exponential type of questions, it's very typical in GATE. At least there are like 1 or 2 questions in each paper. This is also a very straightforward question because all these things in the RHS given, you want LHS. Sometimes n, n0 and t is given, you have to find this lambda, or n, n0 and lambda is given, you have to find the time evolved. Question number 25. The polymeric scaffold has been developed for cartilage tissue engineering. To understand the biodegradability of the material, okay, so we have a question from biomaterials. This polymeric scaffold with a dry weight of 20 milligrams is kept in a lysozyme solution for 7 days. At the end of 7 days, the scaffold is freeze-dried. Dry weight is measured to be 18 milligrams. So we start with 20 milligrams, and after 7 days, it becomes 18 milligrams. Okay. So degradation of the polymeric scaffold after 7 days. All it says is you start with 20 milligrams, it became 18 milligrams. What is degradation? Degradation is essentially the decrease in the quantity of interest, in this case the weight. Okay, and so decrease is 20 minus 18. Okay, and usually expressed in a percentage based on the initial value. So 20 minus 18 by 20, and to make it a percentage, multiply that by 100. And this is 2. So we have 10 and 10 here. So the answer is 10%. Okay. Very, very simple question from biomaterials. Couple of things. Yeah, degradation already says that things are decreasing. So if you were to write, 18 minus 20 by 20 into 100, you will get, I think, minus 10%, which is a wrong answer here. Okay? Degradation doesn't mean change. Degradation actually means decrease. So 10% is the correct answer. Okay? The sign does matter, first thing. Second thing, of course, just like this previous question, now you know a starting value, ending value, and you also know the time passed. You can define something like a degradation rate. That is, what is the rate constant if this were like an exponential decay or degradation? That's also possible. I think there are some questions in GATE 2020 biomedical, and as I said, exponential questions are very, very typical. And this question, of course, is just percentage calculation. Great. Great. So we are heading to 2 more questions. Finally, we are done with all the 1 more questions. So it doesn't mean that we are done with all the easy questions. Actually, there were some really hard questions in 1 marks, and there are some really easy questions in 2 marks. And so questions 26 to 42 will be multiple choice questions. By now we know what is MCQ. So 4 options are given. 1 out of 4 is correct. If you pick the correct option, you get 2 marks. If you pick an incorrect option, you get minus 2 by 3 marks. Okay. So question number 26 from GATE Biomedical 2021. The trace and determinant of a 2 by 2 non-singular matrix A and A or 12 and 32 respectively, eigenvalues of A inverse or dash and dash. So it's very, very typical in GATE. This question based on eigenvalues from linear algebra, this is very, very typical. They will give eigenvalues of some matrix A. They will ask eigenvalues of a function of A. In this case, A inverse. Okay? And this is non-singular, so that you can do A inverse. Just that eigenvalues are not directly given. Trace and determinants are given. So how are trace and determinant going to help us find A inverse? So if you know eigenvalues of A, matrix A, okay, you can easily find eigenvalues of matrix A inverse. That is, these are lambda 1, lambda 2. Eigenvalues here will be 1 by lambda 1 and 1 by lambda 2. Okay, this is very, very easy. Just matrix inverse, the eigenvalue is also inverse. What is given is information on eigenvalues. So trace is nothing but trace of A is just sum of the eigenvalues, lambda 1 plus lambda 2. And determinant of A is just product of eigenvalues. So lambda 1, lambda 2. So 2 equations, 2 conditions on lambda 1, lambda 2 are given. We have to find inverse of lambda 1, lambda 2. Okay, very, very simple. So we know this trace is going to be what? 12, and this determinant is 32. Okay, so let's get rid of this lambda 2. We have 11 plus lambda 2 will be 32 by lambda 1, and that is equal to 12. I have just substituted for lambda 2 here. We get lambda 1 square minus 12 lambda 1 plus 32 is 0. I think this is easily factorizable. Okay, this implies lambda 1 minus 8 into lambda 1 minus 4 equal to 0. So the eigenvalues are essentially 8 and 4. Okay, solutions of this equation. You can call 8 as lambda 1 or 4 as lambda 1. So the other value will be lambda 2. Okay, it doesn't matter. So lambdas are actually 8, 4. How do you get 1 over lambda 1 and 1 over lambda 2? This is 1 over 8 and 1 over 4. Are there any answers here that match it? Yes, 1 over 4 is 0.25. 1 over 8 is 0.12. This is a correct option. Very, very simple to mark from linear algebra, and this is a very, very typical question. Get used to it. So given eigenvalues of A, very, very easy to find eigenvalues of any function of A. That's what this goes down. Question number 27. A unit step input is applied to a system with impulse response h of s is 1 minus s by omega c. Okay, impulse response is given. Output of the system y of t at t equals 0 plus. Okay, so we are given impulse response. We are given what kind of input is there. It's essentially unit step. We want y of t at some particular time. So given information on frequency domain, we want information on time domain. Okay, this is in fact usually an intermediate step in steady state error calculation, but this is actually very easy. This uses a very standard results related to Laplace transform. It's known as the final value theorem, or in this case the initial value theorem. Okay, and these are very simple. All it says is, let's say you know Laplace transform of a function y of s. Okay, finding the value of this function in the time domain y of t at 2 points are very easy. That is, y of t equal to 0 is very easy. Okay, this is nothing but limit s tends to infinity. If you want to find the value at 0, s times y of s. Okay, this is known as the initial value theorem. Of course, if you want to find the value of y at infinity, substitute limit s tends to 0, s times y of s. That's of course one of the final value theorem. Okay, is y of s given here? Yes, using the input and the impulse response, you can find y of s. There is nothing but r of s, h of s, and r of s is given to be, r of s, the input is given to be step. So r of s is essentially 1 over s, and of course h of s is given. Okay, so in this case, the y of t we are interested in. Okay, y of t equal to 0 plus, this is a limit, s tends to infinity. So s times y of s. Y of s is this term. So 1 over s h of s, and that is 1 minus s by omega z by 1 plus s by omega t. Cancel this. Find s tends to infinity. I think you can easily pull out this s. Okay, and similarly pull out this s, and these s's will cancel. S tends to infinity, this term will go to 0, this term will go to 0, only 1 by omega z and 1 by omega p will result. And there will give, and that will give minus omega p will go to the top, and we have omega z in the denominator. So the answer is C. Very simple question. You know, signals and systems or control systems, very typical. In fact, usually they make it slightly harder by asking you to find steady state error. In this case, given h of s, r of s, find y of t equal to 0. Question number 28 from GATE Biomedical 2021. Consider the following first order partial differential equation, also known as the transport equation. So we are given the transport equation. Okay, this PDE is given. With initial conditions are given. This is given to be sin x. X varies from minus infinity to infinity. Value of y of x equal to t at x is pi and t is pi by 6. Yes. Okay, so it's very typical of GATE to frame specifically engineering math questions based on properties. In this case, properties of a PDE called transport equation. Okay, if you know the property, you can write the answer just like that. If you don't know the property, you can spend the entire 3 hours, but it's unlikely that you will find the solution for this. Okay, in this case, you have to use a property of a transport function. Okay, what does a transport function say physically? Let me explain that. So it's a function of 2 variables. Let's say we have some function, okay, f of x, and let's say this is how the function looks at time 0. Okay, so this is x and this is the value of the function. Okay, you can call this y. By transport, it essentially says whatever the shape of this function, imagine a log flowing in a stream of water. Log shape is preserved, right? Just that the log will be at a different place. So similar to that, let's say this were our initial function. This is going to be shifted in time after some time. So this will be f of x comma some other time t. Okay, so this is what the transport equation essentially models. In one way, in other words, okay, the property that this feature boils down to is any function of the type f of x minus ct is a function of this equation, where the c is this constant that shows up over here. Okay? So this is known as the speed at which this function moves, and in this case it's phi. So any function of this form is a solution, and all it says is, so x minus ct, it says the initial function will be, after some time it will be the same function with a time delay. That's what this means. So what is the initial function here? Sin x. So how should this thing solution look after some time? Sin of x minus phi t. Okay. So essentially sin x with a delay. So y of x comma 0 is sin x. Y of x comma t just sin with a delay. What will be the delay? It's phi times t. Phi is the speed of this, speed at which the function traverses. So that's all this. So this is a property we have to use. Essentially, if it's sin x initially, it's going to remain a sin, just that there is going to be a delay. And then, plug in the given values of x and t, you can find this thing. So this is y at pi and pi by 6. And that will be sin of pi minus pi by 6. And this is sin of pi by 6. Sin of 30, which I suppose is half. So it's a value, it's 0.5. So very, very simple question if you know what this transport equation has. So what kind of solutions it has, what that solution means, you can write it down in less than a minute. Else, it's going to be hard to get any marks from this. Of course, even if you don't know any of this, just fill up some value. 1, you see, it's actually pretty close to 0.5. Question number 29. The circuit shown below. Okay, so we are given an unbalanced Wheatstone bridge. Again, this is a typical gate question. In fact, this question was there in one of the mock tests that I gave. And one could use Kirchhoff's voltage law, current law to solve this, but that will take a long time, 5 to 10 minutes. Okay? There is a shortcut to solve this using one of the source transformations, Norton-Thevenin transformations. Try it out. Else, I'll give solutions for this in the subsequent video. Okay. See you again. Wish you all good luck, and hope all of you stay safe. The second wave is getting worse. Many cities are running short of beds. So stay safe, stay at home, take care. I'll see you again. The circuit shown below, VSS 100 volts. Okay, so essentially we have an unbalanced Wheatstone bridge, and I think we want the current flowing through this resistor R3. So VS is 100 volts, okay, and R1 is 30, R2 is 60, R3 is 90, and then R4 is 45, and then R5 is 30. So given this circuit, we want to find the current flowing through this. One way to do this is by using Kirchhoff's first and second law, but that's going to take a lot of time. Specifically, it will take about 5 to 10 minutes. That's not how to approach a gate-to-one question. Here I am going to solve this using a shortcut, using one of the source transformations. Essentially, look at these 2 points, okay? So points A and B. And I'm going to consider R3 as a load, okay? So across these 2 points, can we somehow represent all these resistors R1, R2, R4, R5 along this voltage source using a single voltage source and a single resistor? That is, we want to convert this into a circuit that has essentially the load, that is R3, okay, and rest of the circuit we want to replace that with a single voltage source, okay, and a single resistance. So the 2 points are over here, A and B, and we know the load resistance, this is 90. We want to find an equivalent, okay, resistance here for the entire circuit, And similarly, the equivalent voltage for the entire circuit is known as the Thevenin transformation. Okay? It is across too many points. If you want to represent the equivalent effect of the entire circuit using a voltage and a resistor, this is known as the Thevenin's form. I'm not going to explain how to find VThevenin or Thevenin in general, but I'll explain how to find that for this specific problem. That is, we somehow find RTH and VTH in the equivalent circuit, we can easily find the current flowing through this. Finding RTH is very, very easy. We have to remove the load, okay, and we have to remove any sources. That is, in this case, we have voltage source. We have to short circuit it. So I'm going to draw the equivalent circuit for that. I short circuit the voltage, and then we have the load is removed, and we have these resistors. Now, we somehow find the equivalent resistance of this circuit across A and B. Okay, we'll get the RTH. Interestingly, notice this point is same as this point. Essentially, the top is same as this point. Okay, so in a way, if you label this as point O, okay, I'm going to call this as point O because they are essentially at the same potential. It's the same point. Okay, from R, there are two parallel resistances, R1 and R4 to point O. Similarly, from B, there are two parallel resistances, R2 and R5 to point O. Okay, pause this video, think about it for a moment. Essentially, the equivalent resistance of this circuit about point A and B is going to be, so R1 in parallel with R4, okay, and that is in series with R2 parallel with R5. Okay. So just try to redraw the circuit, noticing that this point has the same potential as this point. You'll quickly end up with this equivalent resistance across point A and B. If it is not apparent, just spend a couple of minutes and I think you can figure it out. So what is this? This is very, very, very simple, right? So R1 30 parallel with 45 plus 60 parallel with 30. So let's quickly calculate this one. This is 30 into 45 by 75 plus 60 into 30 by 90. We quickly calculate what this is. So we have a 3 here, so this is 20, and this is 5, 9. So this is 2 times 9, so it's going to be 18 plus 20. So this is going to be 38. That is, R Thevenin is 38. Okay, so we have found one of the terms in the equivalent circuit. We have to find V Thevenin. V Thevenin is essentially very, very simple. You have to remove the load and actually find the actual potential across A and B using any means. Okay, let's say we remove this load from here and we somehow find VA minus VB. That's very, very simple because this load is removed now. These 2 points are not connected anymore, just like this circuit. Okay, so the voltage here, okay, let's call it VA and let's call this VB. Okay. VA is very, very simple. VA is just, apply voltage divider rule. We have 100 gets divided between 30 and 45. So VA is 100 times 45 by 30 plus 45, which is 75. VB is 100 times, again it gets divided between 30 by 60 plus 30, that is 90. So this is voltage division rule. Okay. So if you know VA and VB, you can find VA minus VB. So this is V Thevenin. Okay. This is VA minus VB. And that from this expression would be so I get 26.67 volts. Okay. So now we know the voltage of the source, equivalent source. We know the resistance. We know the resistance. Can we find I? That is very, very simple. The voltage 26.67 by the total resistance, which is 38 plus 90. What is this? I get 0.211. And Notice, essentially, this is the current that we want. We want the current from A to B, and we already have that I here. So the current from A to B is 0.211, and that's option B. Okay. And also notice the direction of current is given. So this goes from A to B. So based on this, current flows this way, and it's positive. It's 0.211. So this is not the correct answer. Okay. Again, this is my preferred means of solving the problem. If I actually don't have to explain the intermediate steps, you could do it in a minute or less than 2 minutes. Try the same problem using Kirchhoff's voltage and current law. I think you're going to spend a lot of time trying to actually find what this current is. Try it out. For now, this is my quick solution. Question number 30 from Gate Biomedical 2021. X of n is convolved with h of n to give y of n. Okay, so y of 2 is this, y of 3 is this, h of 0. Okay, so NAT type question, we want to find h of 0. X of n is given, h of n is given. We want to find y of, x of n is given, at least all the values are given. X of 0 is this, x of 1 is 0.1. H of n, the values are not given. Interestingly, we have 2 points that are 0. Okay, and some points in the y of n are given. So y of 2 is essentially 1, and the y of 3 is 0. So we know this. Using this information, we have to find h of 0. Essentially, we have to find what is this point over here. So essentially, a convolution, discrete convolution is given. Some data is given. You have to find what is this value. You can write the convolution as a sum, or to make the calculation in the exam. A quick way to do this convolution would be to have this table. So I'm going to write x of n here. So we have x0, x1, x2, and x3. And then I'm going to write h of n over here. So we have h0, h1, h2, h3. Okay. And once you write it, just multiply this row with this value. So, and fill it up over here. For example, h naught times this row, and we know this row. So this is 0, this is 0.1, this is 0.5, and this is 0.4. So this is going to be 0, 0.1 times h naught, 0.5 times h naught, 0.4 times h naught. And this row, of course, is going to be a multiplication of h1, this value. So it's 0 and 0.1 times h1, 0.5 times h1, and 0.4 times h1. And of course, this row is going to be a multiple of this times this, and this row is going to be a multiple of h3 times this. Interestingly, this is 0. Notice h2 is 0, and similarly h3 is also 0. So all these terms will be like 0. Okay. Okay. Once you write this table, it's very easy to find the convolution. Okay. The first term is going to be this sum here. So y of 0 is going to be this term over here, which is 0. Y of 1 is going to be the sum of terms in this diagonal. Okay. That is 0 plus 0.1 times h naught. Y of 3, sorry, y of 2 is going to be the sum of terms in this line, which is 0.1 h1 plus 0.5 h0. Okay. And then we can also write y of 3. This is going to be sum of this line, which is 0.5 h1 plus 0.4 h0. Okay. So once we have this, we also have some additional information of what these are. We know what is y2, this is 1. And we also know what is y3, this is 0. Okay, now we have essentially two equations. Notice we have two unknowns, h1 and h0. And we have two equations, just solve for them and you can get them. Okay. Let me also quickly do that. So can you quickly write h1 in terms of h0? Yes, right. So h1 is minus 0.4 by 0.5. 4 times H0, and what we need is 0.1 H1. So 0.1 H1 is into 0.1. Okay, what we get is this is minus 0.08 H1. So substituted in this equation and we should get this. So this equation says 1 is minus 0.08 H0 plus 0.5 H0. Use this to solve H0. This implies H0 is, which is 2.3. Option D here is the correct answer. Okay. So this is a very simple question from signals and systems doing convolution. This is also very standard. Couple of things. So learn this tabular way of doing convolution. It actually simplify things. If you look at the sum, sometimes it's confusing, but if you just do the sum as a table along the diagonals here, I find it easier. And second thing, try to use as much of information from the question as possible. For example, we know H2 is 0, so don't write this as 0.1 times H2, 0.5 times H2. No, it's 0, so it's 0. Similarly, this row is 0. Okay. Try to do things quickly over here. And this is an interesting question in the sense that it's a nice way of framing a hard question, hard-looking question from a very well-known concept. In this case, which is the convolution, discrete convolution. I would say this is a simple problem, somewhat slightly framed in a less evident way, but that's great for you. Question number 31 from GATE Biomedical 2021. Okay, so we have another question that looks complicated, but I think this question is very, very easy. Okay, in the block diagram shown below, an infinite tap FIR filter transfer function h of z is realized. The transfer function is given. We want the value of alpha. Okay, usually y of z is written as a function of x of z, especially in this FIR filter. It's x of z plus x of z, something like that. Instead of doing that, they have given it as a block diagram. That's all there in this trick. And you have to infer the relation between y of z and x of z using this diagram. Essentially, notice there is a summation here. So x of z goes to y of z. There is an x of z. Okay. Then x of z gets operated by z inverse. So take x of z. Okay. It gets operated by z inverse, and then there is a gain of alpha square. Okay, z inverse alpha square, and that gets summed to y of z. So I have this plus sign here. Similarly, whatever is at this point, which is x of z into z inverse, that's get operated by z inverse again. So what we have here is x of z, z power minus 2. That has a gain of alpha square and again gets summed to y of z. So we have x of z, okay, into z power minus 2 alpha for 4. And this thing goes on and on. So what we have here is x into z power minus 3, that has a gain of alpha power 6, then that gets summed back to y of z. So we have x of z, z power minus 3, alpha power 6. And of course it goes on and on, right? So instead of giving this equation, they have given this block diagram. You have to infer this equation from this block diagram. Once you do that, finding h of z or finding the value of alpha is very, very simple, because can we do h of z from here? Yes. So divide this by x of z, both the sides, okay? Remove x of z, okay? What we end up here is h of z, that is a transfer function. And what we have here, can anyone recognize the form of this summation? It's a simple geometric progression with r as z inverse alpha squared. So this summation, this infinite summation, that's going to be 1 by 1 minus z inverse alpha square, 1 by 1 minus alpha. That's it. So, and this sum is given to be 1 by 1 minus 0.5 times z inverse. So, this term is supposed to be alpha square. So, can you find what is alpha? It is square root of 0.5 or square root of 1 by 2, which is 1 by 2. Option B here is the answer. Essentially, a very simple question on geometric progression, but again, framed in a way such that it looks complicated. But actually, it's a very simple question. In fact, you don't need to know what is an infinite tap, FIR filter, many of these details. Okay, it's an infinite summation sequence. Okay, apply GP, and as far as you know what a transfer function is, which is also given here. Kinda somehow decode what this block diagram means, even if you don't know that. Okay, we have this product here, then there is a gain here, it gets added up here. You can write this term and quickly find what alpha is. Question number 32 from GATE Biomedical 2021. Analog simple. An analog signal is sampled at 100 megahertz to generate 1024 samples. Only these samples are used to evaluate 1024 point FFT. The separation between adjacent frequency points del F in FFT is dash kilohertz. Okay, so we take some analog signal, we sample that at 100 megahertz, and we get 1024 samples. And using these samples, we evaluate a 1024 point FFT, fast Fourier transform. And in this fast Fourier transform, we want to know the del F between, that is the difference between consecutive frequency points. And we want that in kilohertz. There's actually an 1 mark question which shows up as a 2 mark. This is very simple. So we have the sampling frequency, it's called that Fs. Okay, so this is the sampling frequency. Divide that by number of points in the sample, or equivalently the number of points in the FFT, which is 1024 in this case. This gives delta F that they want in this question. Just make sure the sampling frequency is megahertz, so convert that into kilohertz and you get the answer. So this is 100 megahertz is 1000 into 10 power 3 kilohertz, and divide that by number of samples, which is 1024. Quickly calculate this. You get 97.66 kilohertz. That is, yeah, that's it. The answer here is option B. Again, based on some of the 1 mark questions we solved, it doesn't really make sense to have this as a 2 mark. But the trick here is, if you actually know how to find the separation between adjacent frequency points, that is, just take the sampling rate and divide it by the number of samples or the number of points in the FFT, you get the separation. If you don't know that, so I don't know, these are not even traps. So this is a very simple 1 mark question given as a 2 mark. Question number 33 from GATE Biomedical 2021. Okay, this is a question from Opamp in the circuit diagram shown below. All op-amps are ideal. Okay, 3 op-amps, all 3 are ideal with infinite gain and bandwidth. We want V out by Vn for the circuit. So there is usually at least one question from op-amps. You know the basic rules of op-amps. You can easily solve them. Sometimes it also helps to know the gain for standard op-amps. Like inverting amplifier, this is the gain. Non-inverting amplifier, this is the gain. Difference amplifier, this is the gain. Okay. In this case, I think we are given an inverting amplifier here, inverting amplifier here, and then okay, this part we can deal using the standard rules of op-amps, and then we can essentially connect V out and Vn using the standard rules. Okay. So if you know the intermediate gains for these op-amps, for this inverting amplifier, things are going to be faster, and that's how I'm going to solve this. So you start out with B out here. Looks complicated, but can be actually solved quickly. Okay. So we have B out here. Notice, so this is grounded. So virtual short, this is also grounded. So this is also at 0. This is at 0, this is at 0. One of the rules of problems. Okay. And notice this point is at 0, this point is at 0. So we have from here, there's 2R and R. That is, we have these two resistors in parallel going to 0 potential. Okay, that means the equivalent resistance of this is R. Okay, if you have to combine this, it's going to have an equivalent resistance of R. That means the voltage here is going to be, see, R here and R here. So if you do voltage division, this is going to be V out by 2. That will be the voltage here. Okay, you could do that using simple, Kirchhoff current law, but just noticing the symmetry, I wrote this as V naught by 2. You can verify that using, so what is the current here? Current gets equally split between these two, so what should be the potential? Okay, if this is V naught by 2, what should be the voltage here? That can be easily said if you know the gain of this amplifier. Okay, so this is an inverting amplifier. The gain of that V naught by Vn for this bit. Okay, this V naught is not this V naught. So generally, if we have some voltage here, the voltage here are going to be related by minus RF by RI. This is supposed to be RF and this is supposed to be RI. Okay? So essentially the voltage here is going to be, take this voltage, multiply that by R by 2R. So here we'll have minus V naught by 2 times R by 2R. Essentially we have minus V naught by 4. Okay? So this is 2. And if it's minus V naught by 4 here, notice again inverting amplifier with R and R. So the voltage here is going to be simple. Take this voltage, which is minus V naught by 4, then there is a negative sign because it's inverting, and the ratio of these two resistors, R by R. So essentially we have like plus V naught by 4 here. So we have V naught by 4. And we know this is Vn. So these two virtual shorting, or like these two are the same potential. So we know this voltage. So this is at Vi. Okay. And now all we have to do to connect V0 and VAN is to use Kirchhoff current law on this one. The current entering here should be equal to the current that goes here plus the current that goes here. And we know the current that enters this terminal is 0. Another rule of Opamp. So the current that flows here will be V0 by 4 minus VIN. That's the total voltage across this resistor by the value of the resistor. Okay, this is the current that flows towards this node. That should be equal to these two currents. This current is VIN by R plus VIN minus V0. This current VIN minus V0 by 4R. Okay, so R is common, they get cancelled. Let's also get rid of this 4. So this implies V0 by 4 minus VIN. Okay, this is, I'm multiplying everything by 4. So we have 4 VIN plus VIN minus V0. Okay. So let's take it to this side and let's take it V0 to this side. So this implies, I think we have V0 plus V0 by 4. We have 5 V0 by 4. That should be equal to V4 VIN plus VIN. So we have 6 VIN. So V0 by VIN should be equal to 6 into 4 by 5. That I suppose 24 by 5. 5 4s are 20. 5 5s are 25. So something close to 5, slightly lesser. So I think that's option C. Just make sure that's the correct answer. 6 into 4 divided by 5. Yeah, option C, 420. Again, a circuit that looks very, very complicated, but actually, could be done very, very fast. but that involves a lot of tricks, gate tricks. One is notice, okay, I can quickly say this voltage is V0 by 4. Then this is an inverting amplifier, so I know its gain. This is V0 by 2. I know what is the voltage here. Again, I know the voltage here. This is an inverting amplifier. I know the gain of this, so I know the voltage here. So all I have here is, so V0 by 4, V0. Essentially, there are like only the two unknowns here, V0, V out by Vin. Okay. And using just Kirchhoff current law, we can actually find that in 2 lines. Okay. Else, if you have to write Kirchhoff current law in each and every node and try to say whether this input current is 0, whether the output current from an op-amp is 0, get into those confusions, this will take a slightly longer derivation, perhaps 6 to 7 minutes. Still doable. This could be done in 2 minutes. But if you take the other approach, you are likely to make a mistake and it will take 6 to 7 minutes. Question number 34. Okay, this question is from digital electronics. Let's stop the video over here, okay? This, I think, is the most unfair question in the whole paper. Because, this actually, it's not a very simple question. Basically, this body effect is not usually dealt with pen and paper models. Because when you solve problems, this body effect is usually not considered. But in this exam where you have to use a pen and paper to solve this problem, giving this body effect, essentially this connection over here, okay, that makes it really hard. And there are tons of relations, equations for this NMOS, which you'll have to recall. On top of that, you have this strange body effect. Okay? All of that make this question really unfair. Nevertheless, we'll go ahead and solve this just like every other question. But for questions like this, digital electronics, a very good reference is Sedra Smith, microelectronic circuits. In fact, there is at least one digital electronic question from this book, be it diodes, NMOS, okay. One of the examples is usually asked. This is not an example problem, but the relevant theory could be found in this book. Okay? So try all the examples here, which this body effect and all that shows up in some of the advanced chapters. We'll solve the next video with this problem. Meanwhile, try to see if we can actually solve this one.
And currently we are at question number 34. And, this is one of the hardest questions in the whole paper. The circuit diagram shown below, NMOS is in the saturation region. Okay, mu1 COX is this, width is this, length is this. Threshold voltage is 0.4 volts. Ratio of the body effect transconductance to transconductance is 0.1. Small input voltage VAN is applied at the bulk terminal to produce a small change in output voltage Vout. Okay, so this is applied to create an output voltage Vout here. The DC gain for Vout over Vin is dash. Okay. Neglect channel length modulation for NMOS and all intrinsic capacitors. Okay, so I need a lot of space for this. A good reference for this is, of course, Sedra and Smith. Okay, so first thing is we are given this circuit and then, okay, this some conditions and parameters on this NMOS. First, let's make sense out of this circuit over here. Okay, so we have 1.8 volts applied here. So we have 1.8 volts at the top. Okay, and we have 10K, 1K here. Notice for an NMOS, we have the gate here and we have the drain here and we have the source here. This gate current is 0, that is IG is 0. Okay, so whatever current we have here, let's call it IG, that's going to be 0. Because of that, we can apply voltage divider rule here. So this is 10 kilovolts and 10 kilovolts. So this 1.8 will get equally split between these two. So voltage we have here will be 0.9 volts. That is one thing we input here. And
The way to relate B out and B in is through the current in this drain. So that is ID. ID is essentially a function of all the parameters given over here. And in order to explain how ID is related to all these parameters given in the question as well as in the circuit, what is shown here is a symbolic representation of NMOS. I'm going to draw a functional representation of NMOS. This part, this GDS, this NMOS, essentially I have drawn it over here. We have the gate over here. We have the drain over here. We have the source over here. And let's say this body connection, this B, okay, that is over here. Notice, functionally, this is essentially it's a voltage controlled current source. That is, there is current between the drain and source based on voltages at the gate and also at the body. And so there is some current between drain and source that depend upon the voltage between gate and S. Let's call it VGS. Okay, and that current is going to be IGS. That is current that is controlled by the voltage between gate and source. Similarly, there is a part of the current that is controlled by the voltage between body and source. Okay? So we have IBS. This is controlled by the voltage between these two terminals, BBS. Okay? So this is positive, this is negative, this is positive, this is negative. And there are also like some finite resistance effects. Okay, that goes by the name channel length modulation. Okay, because of that, we usually have a finite resistance here, but they say neglect channel length modulation. Because of that, this term is going to be 0. We can neglect this. So essentially, only there is going to be a IGS and IBS. Okay, and the total current that goes into this, notice the current into the gate is 0. So ID will get out here. Okay, and that ID will be the sum of these two currents, IGS plus IBS. This is the first. Can we quickly write what is ID from this circuit? Yes, we can do ID. This is nothing but 1.8 minus V out by this resistance, so 1K. Okay, so if we somehow write IGS and IBS, we have a relation between P out and P in over here. So our IGS is going to be, in terms of all the parameters given over here, this is half of mu COX. This is given to be 200 microampere per whole square into width by length. These are also given here, width by length. Okay, into VGS minus VT square. VGS, do we know the voltage between the gate and the source? Yeah, the source is at 0 and the gate is at 0.9. So this is VGS. Okay, that is 0.9. And VT, the threshold voltage, is given here. Okay, this 0.4 is VT. So this is how IGS depends upon the parameters in the question as well as in the circuit diagram. Then IBS is given by, so IBS depends upon this ratio between GMB and GM. Okay, so we have 0.1 times mu COX, okay, times W by L into, now the voltage at the body is essentially, this is essentially sum of these two voltages, Bn plus 0.5 will be VBS. Okay? So VBS is essentially Bin plus 0.25. I'm going to write that as such, Bin plus 0.25. and this times VOV, or essentially VG minus VT. So VG minus VT. The term that shows up in the square here also shows up here. So we have three relations. One, notice this depends upon V out. Second, IGS, there are no V in terms here, but we have in IBS, we have V in terms. So there is essentially a relationship between V in and V out. So if you simplify this using 1, 2, and 3, what I get is V naught is minus 0.4 times VIN plus 0.7. Just plug in all the parameters with appropriate units. Okay, this is how the final relation simplifies to. That is, this relation simplifies to this. V naught is minus 0.4 times VAN plus 0.4. Now the DC gain is essentially the ratio between V naught and VAN. Okay, essentially this factor over here is the DC gain, and the answer is minus 0.4. Okay. So this term here is DC gain. Now, first thing, so I wish I had actually space to show this simplification, how this thing becomes here, but essentially I have written the appropriate formulae. Okay, try to plug in all the numbers and you should get this simplified relations. If you don't get it, I'll try to post a image of my derivation in the comment section. Here we are at question number 35. As shown in the circuit below, a constant voltage source is connected to two ideal resistors. Okay, we have a constant voltage source and two resistors, 100 and 100. The voltage drop across a resistor is measured using two different voltmeters, V1 and V2, at different time instances. The following values are recorded from V1 and V2. Okay. So recordings from V1 and V1 is here and V2 is over here. Essentially, they measure the voltage across this resistance. So this is an multiple choice question. So out of this four, we have to choose just one. V1 is less accurate, V2 is more precise. Okay, so which of these is more accurate, which of these is more precise? Let's address what is accuracy, and second is what is precision. Accuracy has to do with how close measured values to the actual value. So what is the actual value here? So this is 5 volts. Using voltage divider rule, we know voltage across this is essentially 2.5 volts. So are these values close to 2.5 or these values close to 2.5 volts? So let's see. This is, notice all of them have a difference of approximately 0.03. Okay, and all these are negative. So this is negative, 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 negative. On the other hand, all these readings or the differences from these values to 2.5 is spread out on either side of 2.5. Okay, so if you take 2.5 over here, there are some values on the positive side. Okay, and then there are some values on the negative side. On the other hand, what we have here is, let's say this is 2.5, this is 2.5. All these values are approximately 0.03, and they are all somewhere lumped over here. So accuracy has to do with how close are these measurement values on an average to the actual value. So which of these two cases is more accurate? This case is more accurate, because notice on an average, if you take the average of all these measurements, they are going to be close to 2.5. On the other hand, the average is certainly going to be, a value lesser than 2.5 in this case. So V1 is more accurate, and precision doesn't have to do with the actual value being measured, the true value being measured. Precision has to do with how close are these values to each other. Are these values close to each other? No, because they are like, there is a good spread of all these values. The variance or standard deviation of the spread is higher. On the other hand, notice all of these are close to 0.03. Okay? Okay, so these values are all very close to each other, which means V2 is more precise. Okay, so V1 is more accurate and V2 is more precise. Option B is correct. One way you could quantify this is by using standard deviation, but it's a 2-mark question. You have to make some quick calls. Just see how spread apart these values are and quickly pick an option that works. If you want to quantify it, take average here and take standard deviation here with respect to one of these values. Don't take standard deviation with respect to 2.5. You have to take standard deviation with respect to one of these values. Question number 36 from Grade Biomedical 2021. Closed loop characteristic equation of a system is given by, okay, we have a polynomial. The frequency of oscillations of this closed loop system at steady state is. Okay, so characteristic equation is essentially, let's say it's a denominator of the transfer function, the closed loop transfer function. Oscillations imply there will be complex roots, okay, in the denominator. Complex roots in denominator. And the frequency of these oscillations will be imaginary part of the complex roots. Okay, so for example, if this were a frequency of oscillation, 1j should be a root of this equation. Is that the case? We can quickly test. Okay, what we have here is 1 power 4 j power 4, okay, plus 2 into 1 power 3 j power 3 plus 8 into 1 square plus j square plus 8 into j plus 16. Okay, does this become 0? J power 4 is 1, then j power 3 is minus 2j, j square is minus 8, then we have 8j plus 16. Okay, this is not equal to 0. Had this been a frequency of a steady state, 1j would have been a root of this equation, this characteristic equation. So this is not a root. How about 2? Quickly, 2 power 4 j power 4 plus 2 into 2 power 3 j power 3 plus 8 into 2 power 2 j power 2 plus 8 into 2 into j plus 16. Okay, 2 power 4 is 16, j power 4 is 1. So this is 16. 2, this is 16, and this is minus j, minus 16j. And this is j square is minus 1. This is 2 power 4 is 4. So this is 32. So this is minus 32. Minus 32. And this is 16j plus 16j. And then we have plus 16. Okay, does this become 0? Okay, 16j and 16j cancel. Plus 16 plus 16, that's 32, cancels with minus 32. So this is 0. So this is actually the frequency of oscillation because, okay, this 2j is a root of this equation. You don't have to check 4 and 8 because you already found one solution that's correct. Okay, because this is an MCQ. This is the correct option here. Question number 37 from Gate Biomedical 2021. Match the following in the context of biomaterial characterization. Okay, so we have, okay, so this is a question from biomaterials. We have surface characterization techniques here, SEM, FTIR, X-ray spectroscopy, and AFM. And then we have surface properties over here, elemental composition, roughness, functional groups, topography. This is a hard question in the sense that some of this might have more than one match. Okay? For example, you might think AFM it's possible to measure roughness as well as topography, and then with SEM there are ways to measure, say, elemental composition, then you could measure topography. So for many of this, more than one match seems possible. So a good idea here is to start with something that has only one match. Okay? With FTIR, you could measure, the best thing to measure is the functional groups. And similarly with X-ray photoelectron spectroscopy, the best thing to measure is elemental composition. So these two are clearly one-to-one correspondences. So based on these two correspondences, try to match the other values. So first, QM, so this could be an answer. In fact, none of the other things have a QM. So I think you could go ahead and pick B as a correct option over here. Let's just make sure R is also mapped to K. Okay, we have R is mapped to K. Okay. If we didn't know this map, that is FTIR matches to functional groups, at least if you know X-ray photoelectron spectroscopy matches to elemental composition, you will have to decide between A and B. You could rule out this, you could rule out this, as well as you could rule out this. Question number 38 from GATE Biomedical 2021. In comparison to ECG amplifiers, the surface EMG amplifiers have. Okay, we have to compare gain and then bandwidth. Okay. So ECG and EMG. This is roughly in the order of millivolts, say 0.1 to 5 or 10 millivolts. Okay, and EMG again will be in the same order, 0.1 to 5 or 10 millivolts. Okay. The frequency range of ECG signals will be usually from 0.01 to, let's say, 250 hertz. On the other hand, EMG will have a much wider frequency range. You'll have signals from the DC and up to even like 10,000 hertz. So the amplifiers used should have a comparable gain because the signal values are comparable. So the gain should be comparable. So both of them should have a comparable gain. And then with respect to bandwidth, which one has a higher bandwidth? EMG has higher bandwidth. So EMGs have a comparable gain and a larger bandwidth. So option B is the correct answer. And I also given a list of signal range and bandwidth for many common biomedical signals. Question number 39 from GATE Biomedical 2021. Match the following organs with their functions. Okay, stomach, liver, pancreas, gallbladder, secretion of insulin, profound storage of bile, secretion, bile, gastric. Okay, this is very, very easy. Stomach, it has to secrete gastrin, and then gallbladder doesn't secrete anything. It's the storage device for bile, right? So I think with SL, you cannot actually, SL you can, you have eliminated two options. You can choose between A and B, but SL and PN, okay, we have PN and SL. Okay, and then we have liver, secretion of bile, and then pancreas, of course, secretion of insulin. So option B is the correct one, correct answer. Question number 40 from GATE Biomedical 2021. This is a question from medical imaging, and I think this is directly from Prince and Lens. It's also a very, very easy question. RF pulse is applied to acquire an actual MR image at the ISO center of a 1.5 Tesla MRI scanner with slice thickness 2.5 mm. Assuming a gradient field strength of 2 Gauss per centimeter is applied and gyromagnetic ratio of protons is 42.5 MHz per Tesla, the RF pulse bandwidth required for a slice selection is dash kilohertz. Okay, this is one trick here. So based on the units of the parameters here, you might actually find the answer. Even if you did not know what is bandwidth, the final answer is in kilohertz. You have megahertz per Tesla, and then Gauss per centimeter, and then you have something in meters. So if you multiply all three, you will get it in hertz. And if you take care of the powers of 10, you will get it in kilohertz. Okay. So even if you did not know what is RF pulse bandwidth, you can easily answer this question by checking proper dimensions. Quickly, RF pulse bandwidth. Let's say this is a slice, and the frequency varies between the start of the slice and the end of the slice. So the change in frequency between the start and the end is known as the bandwidth. Okay, and this change in frequency is nothing but the gyromagnetic ratio of the protons times the gradient in field strength. Okay, that is GZ times the thickness of the slice. Okay, that's Z, and this is essentially, you want the final answer in kilohertz. So 42.58 into 10 power 3 kilohertz per Tesla, and then Gauss. So 1 Gauss is essentially 10 power minus 4 Tesla. Okay, so the field strength is essentially 2 into 10 power minus 4 Tesla per centimeters times the slice thickness Z We want this in centimeters so that it cancels. So that is 0.25 centimeters. Notice centimeter, centimeter, Tesla cancels. What we end up with is kilohertz. And quickly check this product. I think I get 2.1299 something. So option B is the correct answer. Yeah, this is a very, very simple question from medical imaging. This is from Princeton Links. Also notice you could answer this question even if you did not know what is this RF pulse bandwidth. Just by doing some dimensional check, that is, you want kilohertz, what do I do with the parameters given in the question to get this dimension? You can actually get the answer. One trick here though is you need to know what is 1 Gauss. That is, you need to know 1 Gauss is 10 power minus 4 Tesla. But even otherwise, the orders of all the variables in this options are all same. So if you assume some 10 power something, still you should be able to get, based on the most significant digits, you should be able to guess that B is the correct option. Question number 41 from GATE Biomedical 2021. Okay, longitudinal pressure. Okay, this question is from ultrasound. And again, this is almost from Princeton Links. There was a very similar question in GATE Biomedical 2020. Just that actually there are so many jargon or terms involved with ultrasound and corresponding formula. We'll get started with the next part by solving this problem.
And here we are at question number 41. The longitudinal pressure wave traveling inside a muscle tissue is incident at an angle of 60 degrees at the interface between muscle and kidney. The wave impedance B, okay, Z kidney, okay, and wave velocities in muscles and kidneys are okay. Transducer center frequency is 1.5 MHz. Pressure wave propagation angle in the kidney tissue and intensity, okay. So there is a longitudinal pressure wave that hits a muscle tissue interface. And we are given information on what is the wave velocity here, what is the impedance here, what is the wave velocity here, what is the impedance here. We are also given the incidence angle. Okay, so it's incident at an angle of 60 degree. And we want two things. One is the pressure wave propagation angle in the kidney tissue. Okay, so once this hits this way, okay, so what will be the angle at which this propagates here in this medium, in the kidney? That's the first thing. And we also want this thing called intensity transmission coefficient. Okay. So had it been the same tissue, it's going to propagate in a straight line. Because the tissues are different, it's going to slightly take a different path. Okay. So this thing usually goes by the name incidence angle. This thing goes by the name transmitted angle. Of course, there is some reflection. This angle goes by the name refraction angle. Okay. So the first part is very, very easy. How do we find this angle? This is very, very simple. We use Snell's law. Okay. Snell's law. All it says is sine theta 1 by sine theta 2 is equal to the ratio between the velocities or the speed in these two mediums. So C1 by C2. Okay. And using this, essentially what we want is this theta 2 over here. Okay. C1 is given to be 1590 and C2 is given to be 1560. Okay. So this is very easy to find. You do theta 2, this is sine inverse of a couple of angles C2 by C1 into sine theta 1. Okay, so this is theta 1, and if you do that, I get 58 degrees. So the first part is very, very simple. So based on the angle, you can actually pick between A and C. You're likely to get positive marks. So even if you don't know what this transmission coefficient is, at this stage, I would just pick one of the options between A and C and move on. But let's also go ahead and see what this transmission coefficient is. See, this intensity transmission coefficient, the amplitude transmission coefficient, then intensity reflection coefficient, amplitude reflection coefficient. All these are typically asked in the GATE exam. Even there was a question in GATE BM 2020 and involves a lot of recall based formula. And the formula changes based on whether the pressure wave hits the interface at an angle or not. What I have given is, I have given pretty much all the formulae involved in pressure wave transmission, reflection, and all that. So take a look at it. And pretty much this is like a concise summary of all the terms involved. So interestingly, many of these terms are known by different names based on the reference book that you choose. What I have done is to consolidate all those terminology as well as all the involved formulae. For GATE, it boils down to recalling all this correct formulae, and I suggest you will have to memorize all this formulae. Okay, for now, the intensity transmission coefficient is 4 zeta 1 zeta 2 cos square theta I by zeta 1 cos square. And we know theta I, which is theta 1. Then we also know zeta 1 is given to be 1.7. Because of the terms involved in numerator and denominator, these powers really doesn't matter. Okay, and zeta 2 is given to be 1.62. If you calculate this expression, I get 0.94. So option C is the correct answer. Question number 42. A novel biomaterial was tested for its tensile properties. The experiment was conducted using a K sample 10 centimeter, all this. Based on the experimental results displayed above, tensile moduli of different tissues are given in the table. Okay, so we are given tissue, bone, tendon, ligament, articular cartilage, and corresponding tensile modulus. Okay, the biomaterial would be essentially they are testing a biomaterial. I think they have given sufficient data to calculate this tensile modulus. Okay, this is just the Young's modulus that you might have come across. Okay, this is just sigma, the stress by the strain. Okay, which could be written as, I think what is given here is they have given diameter, so we can calculate area. They have given the load that is applied. They have given the change in length, and they have also given the original length. So based on the given information, you could write this as stress is just load per unit area, and then strain is change in length per original length. Okay. So this tensile modulus is PL by delta L into A. P is given to be 50 into 10 power 3 newtons. Then L is given to be 10 into 10 power minus 2 meters. Then delta L is given to be 4 into 10 power minus 3 meters. And then A, because diameter is 1 centimeter, A will be pi into 1 into 10 power minus 2 into 1 into 10 power minus 2. So that is 1 into 10 power minus 4. Okay. So this is pi d square by 4. Okay. So there is also a factor of 4 over here. So if you calculate this expression, what I get is 15.9 something. So where does this thing fit? And of course, this is in gigapascal. This is 10 power 9 pascals. So this is 15.9 GPa. It's not MPa. It's not MPa. 0.5 to 1 GPa. No, it's actually more close to a bone because the calculated tensile modulus falls in this range. Okay, 15 lies between 5 and 20 gigapascals. Also notice, so this is diameter, radius is 1 by 2, and accordingly the area is pi d square by 4, which is what I have used here. Very, very simple question. If they ask you, okay, what is the tensile modulus of this material, you might be able to answer it very easily. Just that they are trying to confuse you a bit and frame the question in a data interpretation format. Okay, we are heading to multiple select questions which carry 2 marks each and no negative marks. Essentially 4 options are given, and in that one or more than one option could be correct. Okay, and you have to pick all the correct options to get 2 marks. If you miss any correct option, or if you pick a incorrect option, you don't get any marks, you get 0. Here, question number 43, the circuit shown below, R1, R2, L1, L2 are given. Which of the following describe the characteristic of a circuit? Okay, we have Vs here, input voltage, and then we have the output voltage over here, and this is LR cascaded with LR. If you want to know whether it's high pass, low pass, it's a cascaded circuit, so this is second order. You want to know whether it's high pass, low pass, and then whether it's underdamped, overdamped system. First thing, saying whether it's high pass or low pass is very, very easy. Just look at one of these parts, see whether it's a high pass or a low pass filter. For example, let's say we have B here, then what would be the output voltage here? V0 would be take V and divide it based on these two impedances. So we have R2 by R2 plus SL2. Because we are given AC voltages, I am writing the impedances. Notice as S tends to infinity, V0 tends to 0. Okay, and similarly, if S tends to 0, I think V0 is finite, which means at high frequencies we essentially end up getting no voltage. So we can say that this is a low pass filter because this is a low pass filter, this is a low pass filter, two low pass filter cascaded, we get a second order low pass filter. Okay, so we can say this option is correct, and of course now we can rule out this option. Picking between underdamped and overdamped is going to be slightly tricky in this case. I have been trying to think of a shortcut but not able to find one. Nevertheless, I'll tell you how to do this. The way to do that is essentially to get the transfer function for this system and then look at damping ratio and natural frequency. Okay? So getting the transfer function is going to take some time. You could use Kirchhoff's voltage current law, or in this case, I am primarily going to rely on voltage divider rule. First thing, in order to apply voltage divider, I am going to find the equivalent resistance of this chunk. Okay, so I'm going to call that R pi. R pi is nothing but R1 in parallel with L2 and R2, which are in series. So this will be SL2 plus R2, or R pi will be just R1 into R2 plus SL2 by R1 plus R2 into plus SL2. So how do you write V in terms of input voltage Vx? That's very simple. Take the input voltage and split it in the ratio of this R pi and this total resistance. So split it between R pi and the total impedance, which in this case will be SL1 plus R pi. Okay, now we know V. Can we write V naught? Yes, this is what we have done here. Essentially, so the output voltage in terms of input voltage will be Vs into R pi by SL1 plus R pi. Okay, and this times this term over here, R2 by R2 plus SL2. Now simplifying this is going to take some time. What I have here is V0 by Vs is 2 by S square plus 7S plus 2. From here you can notice that the natural frequency is omega n, and you can use omega n to find the damping ratio. Essentially 2 times damping ratio times omega n is the factor over here, so that is 7. This implies the damping ratio is 2.47. Okay? Damping ratio in this case is higher than 1, which means we are talking about an overdamped system. So this option is also correct. You will get marks only if you pick both B and D. Okay, choosing D is very, very simple. Choosing D is not that straightforward. If there is a shortcut, or if there is some physics in the circuit using which you can certainly say this is going to be an overdamped system, perhaps irrespective of any of these parameters, which is highly unlikely, but just in case there is one, let us know. Let us know of a shortcut in the comment section. For now, this is how you solve the problem.
Question number 44, GATE Biomedical 2021. An inexperienced clinician was measuring cardiac output of a healthy human, okay, by thermodilution, 20 ml cold saline at 7 degrees Celsius. Was injected at the entrance of right atrium. Change in blood temperature at the pulmonary artery was measured to be minus 20 Kelvin second. Cardiac output was calculated using the formula, okay, Q so and so so and so. The clinician realized that there was an error in the measurement of F. Which of the following is true? Now, this is a very, very interesting question because first thing is, this is an MSQ question, right? So out of these 4 options, you have to pick all the options that are correct. And this question is also wrong, in my opinion. Or the question is certainly poorly phrased. Okay, this is a good attempt, but the phrasing could have been improved. So what is going on is some inexperienced clinician is trying to measure cardiac output F using thermodilution technique, and in the process he or she realizes there is some mistake in the measurement, and they ask you, okay, what went wrong? Okay. First thing, a 2 ml of cold saline solution. One of the things is 2 ml is too less for thermodilution techniques. Need at least 5 ml, 5 to 10 ml is what typically used. 2 ml will give you lots of variations and erroneous results. So this is for sure. Cardiac output, okay, cold saline volume was too small. Cold saline volume was too large. Okay, so this is incorrect, certainly. Question is, okay, cold saline volume was too small, so cardiac output is too low. First thing we have to answer this. Right now we know this is too small. And the next thing is, you have to pick between cardiac output is too low or cardiac output is too high. Okay. The thing here is, this integral value is given to be minus 20 Kelvin per second. If you look at temperature variation during normal thermal dilution, say you inject the saline solution over here, there is some variation in the temperature, and then this thing is supposed to go to 0. Perhaps there are some back circulation effects. This is delta T, and this is time. This is essentially the change in temperature you measure in the sensor, and since the time of injection, okay, how does this change vary? And roughly this is about, say, let's say this is 0 seconds. This is something about roughly 20 seconds, and the height over here will be in the order of 0.1 to 0.2 seconds. Okay. If you approximate this by a triangle, half times breadth times height, you get this area to be approximately 2 Kelvin second. Okay, minus 2 based on what the sign of this axis is. What is given here is minus 20 Kelvin second, and so if this value is actually very, very large, if this value is very large, what you measure is going to be very, very small, because you divide thing by a very large number, you get something very, very small. Okay. This is very large. So at this stage, what we can say is that the cardiac output is too low because delta T is too large. Okay. So this option is correct. And then we know the saline volume is too small, but we do not know whether it leads to low cardiac output. So at this stage, we cannot really conclude whether A is correct or not. I think according to official answer key, both A and B are correct. There are lots of problems with this. As I said, we know the cold saline volume is too small, but from that we cannot conclude cardiac output is going to be too low. Okay. I have also given some references for this, some review articles on thermodilution, which says that if you use 2 volume,
variation in the measurement will be very large. That is, the measured cardiac output could be either too low or too high, but we cannot, from this, we cannot directly say that cardiac output is too low. So option A, in my opinion, is not the correct answer. First thing. Second thing, see, this minus 20 Kelvin per second is an intermediate variable. Usually one is not concerned about this value at all. One is concerned about this value measured F. What is likely going on here is that, you know, you are supposed to use a saline solution at, you know, at 0 degrees. But I think due to temperature of the room as well as improper handling of this clinician, that 0 degrees become 7 degrees Celsius before injection. Now the question is, if the clinician knows that the injected saline is at 7 degrees Celsius, the clinician should be able to actually correct for it. So this is written as 7 degrees Celsius, but whether that's known to the clinician or whether it's not known to the clinician, whether the clinician accounted for the term here in this temperature measurement, that is not clearly stated. And the second thing is, you know, one is supposed to know that this value is too large. One doesn't look at this value. One is usually concerned about the cardiac output, which one is trying to measure. Okay, and hardly anyone knows what this area is. Having said that, they gave this value. They expect to know that it's too high, and it's not clearly mentioned whether this 7 degrees was properly accounted in this temperature change calculation. Option B is supposed to be correct. On top of that, they are trying to conclude that using too small volume, you will get to, you know, cardiac output is too low. And had this been two separate sentences, yes, we can make a call on this, but two connected statements, I don't think we can make a call. So my verdict is, this question is wrong. The official answer key is A and B. My answer would be B. And I just try to explain so many things that are actually going wrong here. We tried something very nice. Instead of, you know, asking you to calculate some number based on recalling a formula, we actually gave you the formula and tried to probe further about, you know, what are the things that could go wrong. But I think in the process they ended up with a poorly framed question, and that's my verdict. And this is also the only verdict that's out there, other than just the official key with no explanations. So it's up to you to pick whatever you like. Question number 45 from GATE Biomedical 2021. Again, this is an MSQ. Which of the following statements about smooth muscles are true? Smooth muscles are there in the walls of all hollow organs. Yeah, pretty much blood vessels, stomach, intestine, most hollow organs, the walls are made of smooth muscles. So this is correct. Smooth muscles are controlled by autonomic nervous system. Yeah, something like auto-regulation in blood doesn't happen by our control. It happens through autonomic nervous system. So is digestion, this peristaltic movement and all that. So this is correct. Then smooth muscles are made up of non-striated cells, or smooth muscles are made up of striated cells. Okay. Smooth muscles are made up of non-striated cells. Okay, and so option C is correct. And they are not striated. So option D is incorrect. So for this, A, B, and C are the correct answers. So we are heading to the NAT part in 2 mark session. We have to fill up blanks with numerical answers. We have like 10 questions left. We'll finish it today so that you have at least 1 day for preparation of the mock test. And this is going to be the final video. So we'll complete the paper, and we are at question number 46 and question 46 to 55. So all the questions we'll be solving in this video are of NAT type. So there will be a blank, and you'll have to fill it up with a numerical value. Carry 2 marks each. There's no negative marking. You get 2 marks if you fill up a value that's close enough to the official. Question number 46. Consider a unity feedback system with closed loop transfer function. Okay. The steady state error with respect to a unit ramp input is dash. Okay. So what we are given is a closed loop transfer function. So we have the output here, C of S, and the input here, R of S, and it's a closed loop system. So we have feedback between the output and the input, and this is unity feedback. Okay, so we have a minus here,
what we are given is this ratio between C of S, the output, and the input R of S. The transfer function is given. What we want is a steady state error. Okay. Steady state error, essentially, what is the value of the error at time infinity? Okay. So if E of t is the error signal, we want E of infinity. At this point, we should recognize that this is a very, very typical question asked in the GATE exam. So given something in the frequency domain and we want a time value at either 0 or infinity, we will have to use final value theorem. Okay? So the question is, what is this error signal in this frequency domain? Okay? The error signal is essentially going to be the signal that will show up here for a unity feedback system. Things are slightly different if it's non-unity. That's if we have one more H over here, but here it's just unity. So the signal we get here is the error signal, and notice the error signal essentially will be R minus C. R minus C. Okay. R is the input here, and we take the C and subtract it from R of S to get E of S. So error is just R minus C in unity feedback system, and I'm going to slightly rewrite this. So this is R into 1 minus C by R. Essentially, we have the transfer function that's given over here that shows up that multiplied by R. Is R given? Yes. The input is known as unit ramp. This is R of S is 1 over S square. Okay. So pretty much have all the pieces. Now this is E of S. So how do you find E infinity from E of S? That's, we all know that. E infinity is essentially S E of S. And this should be in the limit. S tends to 0. So this is limit. S tends to 0. S into R of S is 1 by S square times 1 minus S plus 90 by S square plus 10S plus 90. So this is C over R, which is given in the question. Okay. Now we can easily simplify this. So this boils down to limit S tends to 0 over S. This is S square plus 10S minus S, so that will be 9S. Then plus 90 minus 90, that will get cancelled. So S square plus 9S by S square plus 10S plus 90. Okay. So we can pretty much cancel this S and this S. And so what will be left out is S plus 9. As S tends to 0, it will be 9. And then we'll have just 90 in the denominator. So limit will be 0.1. The answer here is 0.1. It's a very, very typical question asked in the GATE exam, because given something is the frequency domain, essentially the Laplace domain, will ask you for some value in the time domain. In this case, steady state error, which is E of infinity, which is S tends to 0, yes, E of S. Question slightly gets tricky if this is a non-unity feedback system. In fact, there is one problem from GATE BM 2020. Take a look at that video. Question number 47 from GATE BM 2021. The diameter of the renal artery, lumen, okay, diameter is 5 mm, mean velocity is 40 centimeter per second, density of blood is, okay, 1060 kilogram per meter cube, viscosity is 3 centipoise. Okay, the Reynolds number of the blood flowing the renal artery is. Very, very simple question. All we need to know is that the Reynolds number is essentially rho u L by mu. Reynolds number, it's a non-dimensional number, so it won't have any units at the end of it. Rho is the density of blood, U is the average blood flow, L is some length scale, usually for Reynolds number it's a diameter, okay? And mu is the viscosity. So the trick here is to actually substitute this in proper units, and it boils down to what we mean by poise. So 1 poise is 0.1 Pascal second. So 3 poise will be 0.3 Pascal second. And so 3 centipoise, just like centimeter, will be 0.3 into 10 power minus 3 Pascal second. Pascal second is in standard units. So if you plug in other things in standard units, in meters and all that. Already things are here in kilogram and meter cube. You should get a non-dimensional value. So rho is 1060. Kilogram is the proper unit for SI. So that times average velocity is 40 into 10 power minus 2 because it's centimeters. And then the length scale is 5 mm. So 5 into 10 power minus 3 by mu. Mu we know is just 0.3 centipoints. Sorry, this is 0.3 10 power minus 2. So this is 0.3 into 10 power minus 2 Pascal second. So if you quickly cancel these things and calculate what this boils down to, I get 706.7. So rounded off the nearest integer, so it would make this 707. So couple of pointers here. This can be written in slightly different forms. For example, there is something called kinematic viscosity. Try to find out what that is. Viscosity instead of the viscosity that is given here. Okay, this has this notation mu. And then sometimes they also replace this average blood flow velocity, this mean velocity, with the flow rate Q, average flow rate Q. Again, look at the relationship between mean velocity and average flow rate, and also look at what is kinematic viscosity mu. Okay? So using this Q and mu, we can get slightly different forms for the inverse number. Question number 48 from GateBM 2021. Drug manufacturer believes there is 95% chance. Okay, there is a long text. At the end of it, we want if the drug is approved by the drug controller, the probability that the drug causes side effects. Okay. Given this, what is the probability of this? So notice, so this is a conditional probability that one. Given something, what is the probability of something else? Okay. So this is conditional probability. And the moment you look at such a phrase, what you should recall is this thing called Bayes theorem. Okay. We'll make a separate video on what is Bayes theorem, but we'll just apply the theorem to solve this particular problem. So to keep things simple, okay, if the drug is approved, okay, make the condition variable A. A is when the drug is approved. And the probability you're looking for, the event that you're looking for, call that B. Okay? This is drug causes side effects. Drug causes side effects. And just name these two, the condition and the probability that we want as A and B. Okay, we work for most Bayes theorem questions. And given this, what we essentially want is probability of B given A. That is the probability of the drug causing side effects given that it's approved by drug control. Okay. Now just do symbolic manipulation here. This is going to be probability of A given B times probability of B by probability of the same term repeated over here, A given B into probability of B plus probability of A given B bar into probability of B bar. So now it's a matter of inferring what all these probabilities are from this particular question. Okay. So we need probability of B, probability of A given B, and then probability of B bar, and then probability of A given B bar. Probability of B is the probability that the drug causes side effects. Here it says that physician working for drug manufacturer believes that there is 0.2 probability that test will show side effects. Okay, so this is the probability of side effects. This is 0.2. Okay, given that the drug shows side effects, what is the chance of, what is the probability that the drug is approved? That is given in this statement. Okay, so P given A is 0.1. And what is the probability that the drug does not cause a side effect? Okay, P of B is 0.2, P of B bar is 0.8, just 1 minus 0.2. And finally, what is the probability that the drug doesn't cause a side effect and the drug gets approved? That is P of A given P of B bar. That is given in this statement over here, which is 0.5. So plug in these values and I think you should get the answer just like that. So this is 0.5 into 0.2 by 0.5 into 0.2 plus 0.8 into 0.9. If you calculate it, what I get is 0.116. So the answer here, rounded off with 3 decimal places, is 0.116. A simple question on base theorem. As I said, make the condition as A, and then the probability for the event that we want as B, then just do symbolic manipulation using standard base theorem. What is base theorem? We'll have to make a very separate video. Question number 49 from GATE Biomedical 2021. The measurement process, groups A and B are recorded. The 10 and 15 values, respectively. Arithmetic means and standard deviations of group A and group B are given. The standard deviation of the combined set of group A and B. So they are essentially made two separate measurements, group A and group B, each with 10 and 15 values. We have given means and standard deviation for the two groups. Now we want the combined. Answer is recall based. We have to use the appropriate formula to find the standard deviation. Let's call this combined standard deviation sigma AB. In order to find sigma AB, we need to first find the combined group means. We call that as mu AB. This is just weighted average of individual means, the weights being the number of values. So this is NA times mu A plus NB times mu B. And of course, this is normalized. So this is NA plus NB. And given mu AB, sigma AB could be easily found. That will be square root of NA into sigma A square plus BA square plus NB into sigma A, so sigma B square plus BB square. Okay. And again, this is normalized. So we have NA plus NB. Sigma A and sigma B are given in the questions. Now, of course, we also know NA and NB. What we don't know is this BA. We want to define that as BA is just the difference between the combined means and the individual mean of group A. Similarly, DB will be the difference between combined mean and mu B. Okay, so let's quickly calculate all these values. What I get for mu AB is 36.8. What I get for BA is 1.8. What I get for BB is minus 1.2. And based on all these values, the combined standard deviation will get us 1.562. That's the answer. 1.56. Yeah, this is a recall based question. I don't think pretty much anyone who gave GATE 2021 were able to recall this particular format during grades. Question number 50 from GATE Biomedical 2021. The circuit given below. Vs is 50 volts. Okay, so this is 50 volts. If the circuit reached steady state for SPDT switch at 1 position 1, switches at position 1, it reaches steady state. Once the circuit is switched to position 2, energy dissipated in the resistors is dash. Okay. So what we have to do was first to find the current in the circuit. When the switch is in position 1, what is the current in this circuit at steady state? And as soon as we change it to 2, how will that current dissipated on these two resistors? It's a very, very simple problem. So first thing is switch in position 1. Further, the circuit is very, very simple. We have a resistor and we have an inductor in series. This is 50 volts and this is 25 and this is 0.1 This is ohm. Notice at steady state, that is T tends to infinity, inductor will be short circuited. So pretty much this part will be short circuited almost as if there is no inductor over there. Okay? at steady state. What it means is that the current here in the circuit will be just 50 by 25, that is 2 amperes. Okay. So this is going to be the current in this circuit, initial circuit at steady state. Now we just make a change in the circuit. So what we do is we go to position 2. So what we have here is resistor, then this inductor, with this resistor over here. So this is 25, this is 25, this is 0.1. And we also know to start with we have a current of 2 amperes. Okay, now you could go try to write an expression for decaying current in a LR circuit and all that, but the energy dissipated in the resistor will be pretty much all the energy stored in this inductor at steady state, which is just half Li square. This will be the energy stored in the inductor at steady state, and this energy will be dissipated through the resistors. So just find this energy. This is going to be half into 0.1 into I square, which will be 2 square. Okay, so the total energy dissipated will be just 0.2 joules. You could go ahead and try to find what is I of t, then try to find the power t of t, then try to integrate the power from 0 to infinity to get actually the energy dissipated in the resistor. It will again give you 0.2 joules. Just notice whatever is the energy that's stored at steady state condition 1, all of that energy will be dissipated in this second circuit. That is, when you move the switch, all of that energy will be dissipated. So the energy dissipated is 0.2 joules. That's the answer over here. Question number 51 from GATE Biomedical 2021. The circuit shown below, the output voltage VO is. Okay, again, it looks like a typical Opamp question. Okay, where we are given an Opamp and then we want to find the VO. But the trick here is, usually in Opamp we only have this negative feedback. In this Opamp, we also have positive feedback. Okay, all these rules of Opamps that things are going to be virtually shorted between this terminal and this terminal, all of those rules don't apply if there is a positive feedback, especially if it's dominant. Okay, so this problem is very, very tricky. At the same time, if you know what the involved trick is, it's also very, very simple. The trick is that you can't apply the standard rules of Opamps, and the simplicity is that, so given this positive loop that actually dominates in this problem, okay, so this Opamp is going to act as a comparator. So essentially, the output of this Opamp will be pretty much like this. It will be 10 volts if the voltage in the positive terminal is greater than voltage in the negative terminal. It will be minus 10 volts, this saturation voltage, if V plus is less than V minus. So which of these two voltages do you think is higher? Of course, the voltage here will be higher compared to the voltage here. Because of that, this value, saturated value, will be reached in this Opamp. Okay, so this is essentially the input voltages, and this is the output voltage here in this Opamp. So the output is going to be this saturated value, which is be minus 10. The simplicity is that it's going to act as a comparator, and so will either give negative saturation or positive saturation based on which voltage is higher. Trick is that you have to realize that you can't apply standard rules of Opamps. Question number 52 from GATE Biomedical 2021. A pacemaker was implanted in a cardiac patient. It has a battery of 2.4 ampere hour. It is designed to deliver a rectangular pulse of amplitude of 0.5 volt 1 millisecond on time for every 1 second. Electrode heart resistance is 150 ohm. Assuming the current drain from the battery is negligible, the lifetime of the pacemaker in years is. Okay, so here what they have given us, so one pulse essentially is 1 millisecond, right? One pulse is 1 millisecond, and after 1 second, it's again going to pulse. So this distance between two pulses is 1 second. So notice the pulse amplitude was 1.5 volts. It's applied to a resistance of 150 ohms. So the current I is just going to be 1.5 volts by 150 ohms. Okay, so this is going to be 0.01 amperes. So for each second, 1 millisecond of 0.01 amperes is going to be applied. And if we use this battery, notice now this area is an ampere second, and this area or this is also in ampere second. Okay, if you convert it appropriately. So how many such areas are there in such a battery? That is what the question essentially asks. Okay, given that, how many time periods can this battery last? That is the lifetime that we are looking for. In other words, okay, one pulse area is just 0.01 into 10 power minus 3. This is 10 power minus 5 ampere second. So how many such areas are there here in this battery? So number of such area, this corresponds to 2.4 into, it's in ampere hour. To convert that into ampere seconds, this is just 2.4 into 3600 ampere second by area of one pulse, that is 10 power minus 5. This value turns out to be 8640 into 10 power 5. So the battery has capacity to sustain these many number of pulses. How much time does these many number of pulses correspond to? Okay, so time corresponds to time, essentially the lifetime corresponds to these many number of pulses, 8640 into 10 power 5. Each pulse is 1 second long, so into 1 second. And let's also convert this into number of years. So these many seconds by 3600 per hour into 24 per day into 365 per year. Okay, so this will be in years, and the value I get for this is 27.4. So the answer here, rounded off to the nearest integer, I think 27 or even 28 works according to the efficiency. So again, this is another typical question, battery life question that is expected in GATE. In fact, this question was there in many of the model test papers that I made. So based on resistance value, how long will the battery last, battery power or battery capacity, how long will the battery last, is a very typical question. And the answer is also very, very simple. Question number 53 from GATE Biomedical 2021. Radiographic system is using X-ray tube operating at 80 kilovolt peak voltage. In order to filter the low energy X-rays, aluminum of 2.5 mm thickness is used. AA filter is replaced with copper, okay, to have the same energy filter. Mass attenuation coefficients of AL and CU are this, densities of AL and CU are this, thickness of the new copper filter is. Okay. All they are saying is, initially they were using aluminum of thickness 2.5 mm. Now instead of aluminum, they want to use copper. And if they want to make sure that the filtered energy is the same, okay, what should be the thickness of copper? This is a very, 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 very simple question. This question was there in one of the mock tests I gave. In fact, including the numbers that are given over here, this is also an example from consumptions. So the energy filtered by the aluminum will be equal to the attenuation coefficient of aluminum times the thickness of aluminum. This will be the energy filter. And we want to make sure it remains the same after using copper. So mu Cu into XCu. The interesting thing is attenuation coefficient mu is not given. Instead of mu, what they are given us mass attenuation coefficient and the corresponding densities rho. You multiply these two, you will get the attenuation coefficient of either copper or aluminum. Okay, so all we have to do to find the thickness of copper XCU is multiply mu AL. I'm going to rho to denote this mass attenuation coefficient, this value times rho AL times X AL by mu CU rho times rho CU. Okay, so what we are given here is the densities rho's, and what we are given here is mu rho, okay, for AL and CU respectively. Just plug in these values and you'll get XCU, and of course XAL is given here. This is XAL. If you plug in all the values, the 5 values here, this 80 peak kilovolt doesn't matter. It's just to make sure that incoming energies are the same. Okay, so just use these 5 values and you should get 0.2 for copper. So the answer here is 0.2. So this is a very simple question. This was expected. This was there in the mock test I gave. It's also an example from examples. Question number 54 from GATE Biomedical 2021. In a radioactive isotope, N nuclei are needed to produce radioactivity level of 2 millicurie, assuming decay constant of this, an atomic weight of 98 gram per mole, Avogadro number, the mass N of radioactive nucleides. Okay. So first thing, the key detail here is to know what is radioactive level and what this unit is. So 1 curie is 3.7 into 10 power 10 decays per second. So let's say nuclei per second. This is what 1 curie is. And this radioactivity level, let's call that as A. This is going to be the number of nuclei times this decay constant. So we have the decay constant lambda. This is lambda, and this radioactivity, the value over here is A. Okay, so given this, we can quickly find what is N. N is just going to be A by lambda. This will be 2 millicurie, so 2 into 10 power minus 3 into 3.7 into 10 power 10 nuclei per second, and divide that by lambda, which is 3.22 into 10 power minus 5 per second. So notice per second it cancels, and what we end up with is nuclei. So these many number of nuclei are there, and to find the number of moles divided by Avogadro number, so what we get is 0.2 into 10 power 23, these many number of moles, and then multiply that by atomic weight. Okay, that is 98 gram per mole. Okay, and what we end up with is grams. So just find this product over here. What I get is 373.9 into 10 power minus 9 grams, or it's essentially 374 picograms. Okay, to the nearest integer. The answer we want here is 374. Very simple question. We need to know what is the radioactivity level and what this unit curie is. So 1 curie is 3.7 into 10 power 10 nuclei per second. Based on that, we can find the number of moles and correspondingly the number of grams. So here are the last question of the series, question number 55 from GATE Biomedical 2021. ECT crystal of thickness 1 mm and wave velocity 4000 meters per second is emitting a longitudinal pressure wave which is incident on a blood vessel at an angle of 30 degrees. Doppler shift in the ultrasound wave for a blood flow of 10 centimeters per second and wave velocity of soft tissue 1540 meters per second is dash curves. A similar question was there in GATE 2020, just that they did not give the frequency of the ultrasound. You have to infer that from some other information given here. Okay, so the Doppler shift FD is going to be 2b cos theta by the wave velocity of the medium times the frequency of the incident wave. Okay, F0. So we know the blood flow velocity. So this is v, We know the soft tissue velocity C0, okay, and we also know the angle theta over here. And the question is, we don't know F0. Instead of that, some information on the PZT transducer is given. Okay, its thickness is 1 mm and its wave velocity within the transducer is 4000 meters per second. Interestingly, using these two information, we can find what is this frequency of this longitudinal pressure wave. Okay, essentially the frequency of the longitudinal pressure wave will be the wave velocity within the transducer, which is, I'm going to call that as C1, that times 2 times thickness of the crystal, okay, 2D. Essentially, so this is going to be 2V by C0 cos theta into C1 by 2D. Okay. So I think last year's question gave F0 directly in the question. This year they gave C1 and D, and you have to find F0. Okay. So now just plug in all the values and you should get the Doppler shift. Okay. So B is going to be 10 centimeters per second. In meters, it's 10 into 10 power minus 2. That times cos of 30 degrees times C1. The wave velocity within the transducer, that is 4000 meters per second. Retain it as such. And C0 is the velocity of ultrasound in the medium. Okay, that is 1540. And the thickness of the transducer, that is given to be 1 mm. So that is 1 into 10 power minus. Just calculate this value. It should be in hertz. And what I got is 225 hertz. So the answer here is 225. This raises a couple of questions. So how do we get this ultrasound frequency is C1 by 2D? Okay, why does it depend on this transducer thickness and all that? Then what is this Doppler shift formula? Where do we get that from? Quick answer, this is there in Enderle and Bronzino as well as in Princeton links. Long answer, you'll have to wait for more videos on theories relating to many of these topics. If you have been learning a lot through this particular series of videos on GATE Biomedical 2021 solutions, and if you want to learn more, so the first thing I recommend is take the mock test that we have scheduled on May 2nd, evening 5:30 to 8:30. And of course, look out for more videos and updates in the channel. I wish you all good luck and I'll see you again.